Look up at the night sky, at that sprawling tapestry of distant suns and swirling galaxies, and you are looking at one of the most profound and unsettling truths of our cosmos. It is not static, it is not standing still. The universe in its entirety is actively, relentlessly expanding, stretching the very fabric of space between all things. For nearly a century, we've known this to be a fact, a cornerstone of modern cosmology, and yet, this simple truth unravels into a labyrinth of deep and puzzling mysteries that challenge the very core of our understanding. What is actually expanding? What is driving this cosmic acceleration? And are we even asking the right questions? This grand expansion is not just a scientific observation. It is a gateway into the most fundamental questions about the nature of reality itself, questions that, the deeper we look, seem to only multiply. Today, we embark on a journey through the greatest unknowns of modern astrophysics, exploring 25 of the most perplexing unsolved questions about the universe's expansion, puzzles that defy our current models and force us to reconsider everything we thought we knew. This isn't just a list of curiosities, it is a voyage to the very edge of human knowledge, where the familiar rules of physics break down and the map of reality turns blank. We will confront the enigma of dark energy, the phantom force that seems to be ripping the cosmos apart. We will grapple with the true shape of the universe and question if our measurements of its expansion are fatally flawed. We will explore the possibility of other universes and ask if our cosmic horizon is merely the edge of a single bubble in an unimaginably vast multiverse. Each question we explore is a thread in a much larger tapestry, a piece of a puzzle that, when solved, could redefine our place in the cosmos. So, prepare to have your perspective shifted, to look at the night sky not as a picture, but as a dynamic, evolving, and deeply mysterious story that we are only just beginning to read. Our journey into the unknown begins with the single greatest mystery in all of modern cosmology, a question so fundamental that its answer would rewrite the textbooks of physics. What, in fact, is dark energy? The story starts not with an answer, but with a shock. In the late 1990s, two independent teams of astronomers were observing distant stellar explosions known as Type 1, a supernova. These cosmic beacons are what scientists call standard candles. Their known intrinsic brightness allows us to measure vast cosmic distances with remarkable precision. The researchers expected to find that the expansion of the universe, set in motion by the Big Bang, was slowing down over time as the collective gravity of all matter pulls inward, acting as a cosmic brake. What they found instead was utterly baffling. The most distant supernova were significantly dimmer than their models predicted, meaning they were farther away than they should have been. The inescapable conclusion was that the expansion of the universe is not slowing down at all. It is speeding up. Some mysterious, unseen force is actively pushing galaxies apart, accelerating the cosmic expansion against the relentless pull of gravity. This discovery was so revolutionary and so counterintuitive that it earned the team the Nobel Prize in Physics in 2011. But the prize was awarded for the question, not for an answer. The force behind this acceleration was dubbed dark energy, and it remains the most profound puzzle in physics today. Think of the universe as a loaf of raisin bread baking in an oven. The raisins are galaxies. As the dough rises, all the raisins move away from each other. Now, imagine that the oven suddenly gets hotter, and the dough begins to rise at a faster and faster rate, forcing the raisins to flee from one another ever more rapidly. Dark energy is that mysterious, ever-increasing heat. It behaves as a form of repulsive gravity, a pressure inherent to the fabric of empty space itself. The most unsettling property of dark energy is its density. Unlike matter or radiation, which become diluted as the universe expands, dark energy appears to maintain a constant density. As the universe grows larger and more volume of space is created, more dark energy comes into existence to fill it. This means that as time goes on, dark energy's repulsive push becomes overwhelmingly dominant over gravity's attractive pull. The most favored theoretical explanation for this bizarre behavior comes from an idea proposed by Albert Einstein himself long before the accelerating universe was discovered. He introduced a fudge factor into his equations of general relativity called the cosmological constant, a sort of energy intrinsic to the vacuum of space that could produce a repulsive gravitational effect. For Einstein, it was a way to force a static, unchanging universe, a notion he later called his greatest blunder after Edwin Hubble discovered the universe was indeed expanding. Yet now, the cosmological constant appears to be the simplest explanation for dark energy. The problem is, when physicists try to calculate the expected value of this vacuum energy using our best theory of the small-scale world, quantum mechanics, the number they get is wrong. Not just a little wrong, but catastrophically, inexplicably wrong. The theoretical prediction is about 120 orders of magnitude. That's a 1 with 120 zeros after it, larger than what we observe. This is arguably the worst mismatch between theory and experiment in the entire history of science. If the quantum calculation were correct, the repulsive force would have been so immense that it would have torn apart stars, planets, and even atoms before they could ever form. The fact that we exist to ponder the question means our understanding of the vacuum of space is fundamentally incomplete. So here we stand. Dark energy constitutes about 68% of the total energy budget of the entire universe. It dictates the ultimate fate of the cosmos, yet we have no definitive idea what it is. It could be a constant energy of the vacuum, as the cosmological constant suggests. It could be a dynamic, evolving force field that has changed over cosmic history, sometimes called quintessence. Or it could be something even more exotic, a sign that Einstein's theory of gravity, while brilliant, breaks down on the very largest scales. The nature of dark energy is not just question number one on our list. It is the central enigma around which all other mysteries about cosmic expansion orbit. But this leads us directly into our second great mystery, a question that probes even deeper into the strange nature of dark energy. If we accept that this force is real, we must then ask, is the cosmological constant truly constant, or could the strength of dark energy itself be changing over time? The idea of a truly fixed cosmological constant is elegant in its simplicity, but many physicists find it unsatisfying. Why should this dominant component of the universe be so perfectly, unchangingly static? This has led to an alternative and in many ways even more intriguing proposal, a concept known as quintessence. Imagine quintessence not as a steady, immutable force, but as a dynamic, cosmic field that permeates all of space, a kind of fifth fundamental force whose energy and pressure can slowly evolve as the universe ages. Unlike the rigid cosmological constant, quintessence is a theoretical fluid that could either weaken or strengthen over billions of years. This single possibility opens up a spectrum of dramatically different futures for our cosmos, each more extreme than the last. If dark energy is constant, the universe's expansion will continue to accelerate forever. Galaxies outside our local group will eventually be pushed so far away that their light can no longer reach us, leaving our descendants in a vast, lonely, and ever-darkening island universe. But if quintessence is real and its repulsive power increases over time, we could be facing a far more violent end, the Big Rip. In this scenario, the accelerating expansion doesn't just push galaxies apart. It eventually becomes so powerful that it overcomes all the forces that hold things together. First, galaxy clusters would be torn apart, then individual galaxies. As the force grows, gravitational bonds holding stars and planets together would snap. In the final, terrifying moments, the fabric of spacetime itself would tear apart, ripping atoms and even subatomic particles into nothingness. The entire universe would be shredded in a final, catastrophic instant. On the other hand, what if this quintessence field weakens over cosmic time? It could decay, or its repulsive effect could even reverse, becoming attractive. This opens the door to a classic, if equally dramatic, fate, the Big Crunch. In this model, the current acceleration of the universe would be a temporary phase. Eventually, dark energy would fade, allowing gravity to reassert its dominion. The expansion would slow, halt, and then reverse. The universe would begin to collapse in on itself, with all galaxies rushing back toward each other. The cosmos would heat up, the background radiation would blue shift, and everything would ultimately be compressed back into an ultra-hot, ultra-dense singularity, a mirror image of the Big Bang, potentially setting the stage for a new cosmic cycle. The key to figuring out which of these futures awaits us lies in making increasingly precise measurements of the expansion rate across cosmic history. Astronomers are using everything from distant supernova to the large-scale structure of the universe, mapping the distribution of galaxies to see if the equation governing dark energy has changed over billions of years. So far, the data still agrees with a simple cosmological constant, but the uncertainties are large enough to allow for these more exotic possibilities. The hunt is on to see if the engine of cosmic expansion has a fixed throttle, or if it's a dial that is slowly, imperceptibly being turned. This leads us directly to a question that has haunted philosophers and scientists for millennia, a query that is now firmly in the realm of observational science. What is the ultimate fate of the universe? The answer is not written in stone, but in the subtle, evolving behavior of dark energy, and depending on its true nature, the final chapter of our cosmos could range from a quiet, frozen eternity to a sudden, violent end. The most widely accepted scenario, based on our current best data, is known as the heat death or the Big Freeze. Picture a universe where the acceleration continues unabated, driven by a constant dark energy. Galaxies beyond our own local group would first redden, then fade from view entirely as the space between us expands faster than light can traverse it. The cosmic horizon would shrink around us, isolating our galaxy in an ever-expanding void. Inside galaxies, stars will continue to burn out one by one. After trillions of years, the last stars will flicker and die, leaving behind a cold, dark cosmos populated by black holes, neutron stars, and frozen stellar remnants. Even these will not last forever. Over staggering timescales, black holes themselves will slowly evaporate due to a quantum process known as Hawking radiation, dissolving into a faint mist of particles. The universe would approach a state of maximum entropy, a final equilibrium where the temperature uniformly approaches absolute zero. Energy would still exist, but it would be spread so thinly that no work can be done, no structure can form, and no further change is possible. It would be a cosmic graveyard, silent, dark, and eternal. But what if dark energy is not constant? This is where the future becomes far more dramatic. If dark energy is a form of quintessence that grows stronger over time, we face the terrifying prospect of the Big Rip. In this scenario, the accelerating expansion doesn't just affect the distances between galaxies, it eventually overcomes every single force that holds the universe together. First, the gravitational glue binding galaxy clusters would be overwhelmed, flinging them apart. Then, individual galaxies would be torn asunder, their stars scattered into the void. As the repulsive force intensifies, it would target smaller and smaller structures. About 3 months before the end, in this hypothetical timeline, the solar system would be ripped apart. In the final minutes, stars and planets themselves would be shredded. An instant before the end, the expansion force would exceed the strength of atomic bonds, tearing molecules apart. Then it would overcome nuclear forces, ripping atoms and nuclei to pieces. In a final, unimaginable flash, the very fabric of spacetime itself would be torn apart, ending the universe not with a whimper, but with a definitive, catastrophic singularity. This stands in stark contrast to a much older, almost cyclical vision of cosmic destiny, the Big Crunch. This model requires that dark energy is not a permanent feature but a temporary phase. Perhaps the quintessence field decays, or the cosmological constant isn't constant after all. In this future, the acceleration would eventually slow, stop, and then reverse. The universe would begin to collapse under its own gravity. What was once a red shift as galaxies fled would become a blue shift as they rushed back together. The temperature of the cosmos would rise, first slowly, then precipitously. The cosmic microwave background radiation would heat up from its current few degrees above absolute zero to eventually outshine the surfaces of stars. Galaxies would merge and the universe would become a seething, hot soup of particles. Finally, everything would be compressed into an ultra-hot, ultra-dense state, a singularity mirroring the Big Bang itself. This idea of a collapse naturally sparks one of the most profound speculative concepts in all of cosmology, the cyclic universe. Could the Big Crunch simply be the precursor to another Big Bang? Is our universe part of an endless, eternal cycle of expansion and contraction, a cosmic phoenix repeatedly rising from its own ashes? Some theoretical models, like conformal cyclic cosmology or those involving colliding brains in string theory, suggest this is possible. In these visions, the universe has no true beginning or end, only an endless sequence of eons, each one giving birth to the next. The information from the previous cycle could, in some way, be imprinted on the next, creating a potentially eternal recurrence. This dizzying array of possibilities highlights a truly humbling fact. The ultimate fate of everything we know hinges on properties of dark energy that we have not yet measured. Is its equation of state parameter exactly -1, indicating a true cosmological constant, or is it slightly different, pointing toward a dynamic quintessence? Our current uncertainty means that the final destiny of the universe, whether it ends in ice, fire, or rebirth, remains one of the greatest open questions in all of existence. But to truly understand these grand, sweeping visions of cosmic destiny, we need to get the numbers right. We need to know with precision exactly how fast the universe is expanding today. And this brings us face to face with one of the most stubborn and significant problems in modern cosmology, a puzzle known as the Hubble Tension. The story begins with Edwin Hubble's landmark discovery in the 1920s that the universe is not static, that distant galaxies are all rushing away from us with their speed of recession proportional to their distance. This relationship is encoded in a single, crucial number, the Hubble constant. It is the current expansion rate of our cosmos, the very metric that tells us how fast space is stretching at this very moment. For decades, astronomers have worked to measure this number with ever greater accuracy, assuming that different methods would eventually converge on a single, agreed-upon value. Instead, they have driven headlong into a contradiction. When we measure the Hubble constant by looking at the local, modern universe using what are called the cosmic distance ladder techniques, we get one answer. But when we measure it by looking at the infant universe using the afterglow of the Big Bang itself, we get a different, stubbornly inconsistent answer. It is as if you calculated the age of a tree by counting the rings near its bark and got one number, but then calculated it by measuring the isotopes in its very core and got a significantly different result. This is not a small, marginal error that can be brushed aside. The discrepancy is now measured with such high precision that the chance of it being a simple fluke is less than 1 in a million. This is a genuine crisis, a crack in the foundation of our standard model of cosmology that suggests we might be missing something profound. The first method, the local measurement, relies on building a cosmic ladder step by step. Astronomers start with nearby stars, such as Cepheid variable stars, whose predictable pulsations allow us to determine their true brightness. By comparing that known intrinsic brightness to how dim they appear from Earth, we can calculate their distance with high confidence. Then we look for these same Cepheids in more distant galaxies that also host Type 1a supernova. Since we now know the distance to those galaxies from the Cepheids, we can calibrate the true brightness of the supernova. Finally, we look for these supernovae in galaxies so far away that their light has been traveling for billions of years. Because we know exactly how bright these supernovae are, their apparent dimness tells us their distance, and the redshift of their host galaxies tells us how fast they are moving away. This entire intricate chain gives us a direct measurement of the expansion rate in our cosmic neighborhood. The result from this method is a universe expanding at about 73 kilometers per second per megaparsec. This means that for every megaparsec, about 3.26 million light-years, you move away from us, a galaxy appears to be moving 73 kilometers per second faster. The second method takes a completely different approach, using the universe's baby picture, the cosmic microwave background. This faint, all-sky glow is the cooled and stretched remnant of the hot, dense plasma that filled the cosmos about 380,000 years after the Big Bang. By mapping the tiny temperature fluctuations in this background radiation with exquisite detail, as missions like the Planck satellite have done, we can discern the precise physical conditions of the early universe. We can see the imprint of sound waves called Baryon acoustic oscillations that were frozen in place when light finally broke free. The scale of these ripples acts as a cosmic ruler. Using our immensely successful standard model of cosmology, which includes dark matter and dark energy, we can run the clock forward from that infant state to predict what the expansion rate should be today. This prediction is unwavering, about 67 kilometers per second per megaparsec. The gap between 73 and 67 is small in absolute terms, but in the world of precision cosmology, it is a chasm. This is the Hubble tension. It means that the universe today appears to be expanding significantly faster than our best model of the early universe says it should be. So, what could be causing this? Perhaps there is an unknown systematic error in one of the measurements. Maybe our understanding of Cepheid variables or supernova is subtly flawed, or our interpretation of the cosmic microwave background has a hidden blind spot. But after years of scrutiny, no one has found a convincing error. The measurements have only become more robust and the tension has tightened. This leads to the thrilling possibility that the discrepancy is real and that it is a signal of new physics. Our standard cosmological model, for all its success, might be incomplete. Maybe dark energy is not a simple cosmological constant but is evolving, becoming stronger in the recent cosmic past. Perhaps there is a new, previously unknown type of subatomic particle that flooded the early universe like a form of dark radiation, which would alter the rate at which the cosmos expanded in its youth and thus change the prediction for today. Or this could be a hint that the dark matter particle has properties more complex than we currently assume. Some have even suggested more radical ideas, like a slight, early lumpiness in the distribution of matter that we haven't accounted for. The Hubble tension is more than just a debate over a number, it is a direct challenge. It tells us that our most cherished model of the universe, pieced together over decades of observation, might have a fundamental flaw. Unraveling this single mystery could open a window into physics beyond our current understanding, revealing new cosmic ingredients or forces that have, until now, remained completely hidden from view. This discrepancy in the Hubble constant forces us to confront a deeply unsettling possibility. What if our entire understanding of the universe's infancy is fundamentally flawed? The cosmic microwave background is our most trusted window into the early cosmos, a pristine snapshot from a time long before the first stars ignited. We have built our entire standard model of cosmology upon the precise patterns etched into this ancient light. but the Hubble tension suggests this foundation might have a hidden crack. Perhaps the universe's first chapter contained plot twists we never anticipated, involving unknown particles, fleeting forces, or even a miscalibration in how we read this cosmic relic. One compelling line of investigation points to the possibility of exotic ingredients in the primordial cosmic soup. Our models assume that the early universe was filled with a known roster of particles, photons, neutrinos, dark matter, and the building blocks of atoms. But what if there was an extra component, something that behaved like radiation but has since vanished? Theorists call this dark radiation, often symbolized by the effective number of neutrino species. We currently base our calculations on 3 known types of neutrinos, but if there were actually a 4th or even a fraction of an additional type, it would have altered the very timing of key cosmic events. More radiation in the early universe would have caused it to expand faster in its first few 100,000 years. This would change how we interpret the size of the ripples we see in the cosmic microwave background. When we then use that data to predict the expansion rate today, we would get a higher value for the Hubble constant, potentially bringing it much closer to what we measure locally. This wouldn't just be a minor tweak, it would be an admission that the particle content of the infant cosmos was richer and more complex than our standard model of particle physics allows. Another radical idea suggests that dark matter itself might not be as simple and inert as we assume. The prevailing view is that dark matter is cold, meaning its particles moved slowly in the early universe, allowing structures to clump together easily. But what if a portion of dark matter was slightly warm, or even interacting? If dark matter particles could interact with each other or with radiation through some unknown force, it would have smoothed out the small-scale clumpiness of the early universe. This change in the initial distribution of matter would directly affect the pattern of sound waves imprinted on the cosmic microwave background. Recalculating the evolution of the cosmos with this modified dark matter could, in theory, resolve the tension by adjusting the predicted expansion rate to match our local measurements. It's a scenario that forces us to reconsider the nature of the universe's most dominant form of matter. Beyond new particles, we must also consider the raw energy that powered the universe's birth. The prevailing theory of inflation, a period of fantastically rapid expansion in the first fraction of a second, sets the initial conditions for everything that followed. But what if inflation was slightly different than our simplest models suggest? Perhaps the energy field that drove inflation had a more complex shape, leading to a subtle change in the strength of gravitational waves it produced, or a minor alteration in the way quantum fluctuations were stretched into the seeds of galaxies. Any such deviation would propagate through cosmic history, changing the predicted Hubble constant. The tension we see today could be an echo of inflation's true, more complicated nature. There's even the more straightforward, yet equally troubling, possibility that we are misreading the cosmic microwave background itself. Our maps from the Planck satellite are incredibly precise, but turning that raw data into cosmological parameters requires a complex chain of analysis and assumptions. Could there be an unaccounted for systematic effect, perhaps from foreground dust in our own galaxy or from the instrument itself, that subtly biases our results? While the Planck team has rigorously tested for such issues, the persistence of the tension keeps this door open. It suggests that the universe's baby picture might have a faint smudge we haven't yet cleaned, a smudge that, once removed, could reveal a cosmos that is perfectly consistent from its beginning to its present day. Ultimately, the Hubble tension is a powerful reminder that our models are only as good as the assumptions they rest upon. The early universe is not a directly observed historical event. It is a reconstructed one based on the fossil evidence we find today. If that reconstruction is wrong, then our entire timeline of cosmic evolution needs a revision. The quest to solve this puzzle is not just about reconciling two numbers. It is a direct investigation into the physics of the first moments of time, an exploration that could uncover new chapters in the story of our cosmos that we never knew were there. Now let's turn to a question that is almost impossible to visualize, yet lies at the very heart of cosmology. What is the actual shape of the universe? We often picture space as a vast, empty, three-dimensional stage where galaxies are placed, but general relativity tells us this stage itself has a geometry. It can be curved by the matter and energy within it, meaning the entire cosmos could, in principle, have a global shape. Scientists have narrowed the possibilities down to three primary geometries, and which one is correct depends on a single critical number, the average density of the universe. If the density is exactly equal to a specific critical value, the universe is flat or Euclidean. In a flat universe, the rules of geometry you learned in school hold true on the largest scales. Parallel lines never meet. The angles of a triangle always add up to 180 degrees, and space extends infinitely in all directions. If the density is higher than this critical value, the universe takes on a positive curvature, making it a closed geometry, analogous to the surface of a sphere, but in 3 dimensions, not 2. In this spherical universe, parallel lines would eventually converge. The angles of a triangle would add up to more than 180 degrees, and the cosmos would be finite in volume, yet without any edge. If you could travel in a perfectly straight line for long enough, you would eventually circumnavigate the entire universe and return to your starting point, much like an airplane flying around the Earth. Finally, if the density is lower than the critical value, the universe would have a negative curvature, forming an open, hyperbolic shape, often compared to a saddle or a Pringles chip. In this vast, open geometry, parallel lines would diverge. The angles of a triangle would sum to less than 180 degrees, and space would be infinite and expanding forever. For decades, the quest to measure this cosmic density and thus determine the shape of the universe was one of astronomy's holy grails. The answer came from a seemingly unlikely source, the faint, ancient glow of the cosmic microwave background. The tiny fluctuations in this radiation, the frozen sound waves from the early universe, act as a cosmic ruler. The apparent size of these ripples on the sky is exquisitely sensitive to the overall geometry of space through which that light has traveled for 13.8 billion years. In a curved universe, whether spherical or hyperbolic, these ripples would appear distorted to us, their apparent size either magnified or minified by the curvature of spacetime itself. After painstaking measurements from satellites like WMAP and Planck, the result was clear and astonishingly precise. The universe appears to be flat, or so nearly flat that we cannot measure any deviation. This finding is monumental, as it implies that the total density of the cosmos is at, or extremely close to, the critical value. This perfect balance seems almost too good to be true, and it leads directly to one of the earliest puzzles of modern cosmology, the flatness problem. Why is the universe so exquisitely flat? The initial conditions at the Big Bang would have had to be fine-tuned to an unimaginable degree to result in such a balanced cosmos today. A tiny deviation in density in the early universe would have been amplified over billions of years of expansion. If it were slightly denser, the universe would have collapsed back in a big crunch long ago. If it were slightly less dense, it would have expanded so rapidly that galaxies and stars never could have formed. The fact that we see a universe so perfectly poised between these two extremes cries out for an explanation, and the leading theory that provides one is cosmic inflation. That brief period of hyper-expansion in the first fraction of a second would have stretched the fabric of space so tremendously that any initial curvature would have been flattened out, like blowing up a balloon to the size of the observable universe and finding the surface locally appears flat. While the evidence for a flat universe is strong, it is crucial to understand what this flatness actually means. When we say the universe is flat, we are referring to its spatial geometry on the largest observable scales. This does not, however, necessarily mean the universe is infinite. It is entirely possible for the universe to be finite and yet still be flat if its overall topology is complex. Think of a perfectly flat piece of paper. Now imagine rolling that paper into a cylinder and connecting the ends. The geometry is still locally flat. The rules of Euclidean geometry hold, but the space is finite because if you travel in one direction, you return to your starting point. Our universe could, in principle, have a similar multi-connected topology like a three-dimensional torus. The fact that we haven't observed any repeating patterns in the cosmic microwave background that would betray such a structure places lower limits on the size of the universe, but it doesn't rule out that the entire cosmos could be many times larger than what we can observe while still being finite. This leads to a profound implication for expansion. The geometry and fate of the universe are deeply intertwined. A flat universe with its critical density is poised to expand forever, but at a rate that gradually slows towards zero, a fate sealed by the presence of dark energy which now dominates and drives the accelerated expansion. In a closed, spherical universe, the expansion would eventually halt and reverse into a big crunch. In an open, hyperbolic universe, expansion would continue relentlessly. Our measurement of flatness, combined with the discovery of dark energy, tells us we are in that first category, a flat universe destined for perpetual, accelerating expansion. Yet a shadow of a doubt remains. The measurements, while incredibly precise, still have margins of error. It is still possible, though unlikely, that the universe has a very slight positive or negative curvature that is simply too small for our current instruments to detect. If future observatories were to find even a tiny deviation from perfect flatness, it would force a major revision of our standard cosmological model and could alter our understanding of the universe's ultimate size and fate. The shape of the cosmos is not just an abstract geometrical curiosity. It is the canvas upon which the entire history of the universe is painted, determining its past, its present, and its final destiny. Building directly from our picture of a geometrically flat cosmos, we are led to one of the most mind-bending questions humanity has ever asked: is the universe infinite? The data suggesting a flat or nearly flat geometry points toward a cosmos without spatial curvature, and within the framework of Einstein's equations, a flat universe is most naturally an infinite one. Think of an endless, featureless plane extending in every direction without bound. If the universe is indeed perfectly flat, then it has no edge, no boundary, and no center. It simply goes on forever, with galaxies, stars, and potentially even planets and life, stretching out into an unending cosmic tapestry. This is not merely a large number. Infinity is a concept that defies our everyday intuition. We can comprehend vastness, a billion galaxies, a trillion stars, but true infinity is qualitatively different. It suggests that every possible configuration of matter, every conceivable arrangement of atoms, must occur not just once, but an infinite number of times. Somewhere in the unfathomable vastness of an infinite cosmos, there could be an exact duplicate of our Earth, of you, and of everyone you know, living out a life identical to yours in every detail, or perhaps differing in the slightest trivial way. This staggering idea, emerging directly from the physics of a flat, infinite universe, is known as the cosmological ergodic theorem. While it sounds like science fiction, it is a serious, if profoundly unsettling, implication of our best models. Yet the concept of infinity is not just a philosophical curiosity. It presents concrete physical challenges. If the universe is infinite and filled with stars and galaxies, then every line of sight should eventually end on the surface of a star. The entire night sky should be as bright as the surface of the sun, a paradox known as Olber's paradox. We know this isn't the case, and the resolution lies in the universe's dynamic nature. The universe is not infinitely old, and its expansion dilutes and redshifts the light from distant stars, plunging the space between galaxies into darkness. The finite age of the cosmos and the speed of light create a visible horizon, a limit to what we can observe, shielding us from the full, blinding glare of an infinite stellar population. But here we must make a crucial distinction, one that is central to modern cosmology: the difference between the entire universe and the observable universe. Our observable universe is a finite sphere about 93 billion light-years in diameter, centered on Earth. It contains everything whose light has had time to reach us since the Big Bang. This is our cosmic backyard, the only part of the cosmos we can ever hope to see or measure. However, if the larger universe is indeed infinite, then our observable universe is just an infinitesimal speck within a boundless whole. The galaxies we see are merely our local neighborhood. Beyond our cosmic horizon, space continues, filled with more galaxies, more stars, and potentially more planets forever. This leads to another profound possibility: that the universe, while spatially flat, could still be finite in size if it has a multiply-connected topology. Imagine the geometry of a video game world, where if you travel off the right edge of the screen, you reappear on the left. The space is locally flat. The geometry works just like an infinite plane, but it is finite because it wraps around on itself. Our universe could, in principle, have a similar shape, like a three-dimensional torus. If this were the case, and the universe were small enough, we might see the same galaxy or cluster of galaxies in multiple different directions in the sky, like a cosmic hall of mirrors. Astronomers have searched for such repeating patterns in the cosmic microwave background and large-scale galaxy surveys, but so far none have been found. This places a lower limit on the size of the universe. It must be at least hundreds of times larger than our observable horizon. It could still be finite, but on a scale so vast that it is, for all practical and philosophical purposes, indistinguishable from infinite. The ultimate answer to this ancient question, therefore, hinges on a measurement of breathtaking precision, determining if the universe's flatness is perfect. Our current data says it is flat to within a margin of error of about 0.2%. But is it exactly flat? A perfectly flat universe almost certainly implies an infinite one. A universe with even the tiniest positive curvature, 1 part in 100,000, would be a closed sphere, finite and ultimately bounded. Detecting such a minuscule deviation is at the very limit of our technological capabilities, a challenge for the next generation of cosmic observatories. To contemplate an infinite universe is to confront the limits of human comprehension. It challenges our sense of place and significance, suggesting that our entire cosmic history is just one of an endless number of identical narratives playing out across an eternal stage. Yet, it is a possibility that our most successful scientific theories point toward, a breathtaking conclusion drawn from the subtle geometry of the cosmos itself. Now, just as we grapple with the universe's shape and size, we must rewind the cosmic clock all the way back to its very first moments, to a period so brief and so violent that it defies comprehension. We arrive at the theory of cosmic inflation, a concept that attempts to answer some of the most fundamental questions about our origins. The standard Big Bang model is incredibly successful, but it leaves several nagging puzzles unexplained, like the flatness problem we just encountered. Why is the universe so perfectly balanced? Inflation provides a stunningly elegant solution. It proposes that a fraction of a second after the universe began, perhaps at around 10 to the power of -36 seconds, the cosmos was seized by a peculiar high-energy state that caused it to expand at an exponential, faster-than-light rate. This wasn't expansion in the way we see today, with galaxies drifting apart in already existing space. This was the rapid, mind-boggling stretching of the fabric of spacetime itself. In an almost unimaginably short span, a region of space smaller than a subatomic particle was inflated to a size larger than our entire observable universe. This explosive growth solves the flatness problem in one stroke. Think of the surface of a crinkled, wrinkled balloon. As you inflate it to an enormous size, any small section of its surface becomes flatter and flatter. Inflation did the same thing to the cosmos, stretching any initial curvature so thin that the universe we inherited appears perfectly flat on large scales. But what is the evidence for such a fantastical event? The most compelling proof comes from the cosmic microwave background. This ancient light is incredibly uniform, with a temperature that is the same in all directions to within tiny fractions of a degree. This presented a major conundrum known as the horizon problem. Regions of the cosmos on opposite sides of the sky were never close enough to have exchanged heat and reach a common temperature, according to the standard Big Bang timeline. Their light is only just reaching us now. How could they possibly be in thermal equilibrium? Inflation provides the answer. Before the inflationary burst, the entire observable universe was a tiny, subatomic-sized patch that was causally connected, meaning all its parts were in contact. This region was in thermal equilibrium. Then, inflation took this tiny, uniform patch and stretched it to a cosmic scale, preserving that initial uniformity across the vast expanse we see today. The universe is so uniform because it was once so incredibly small. Furthermore, inflation doesn't just predict a smooth universe, it predicts the exact right kind of imperfections. The quantum vacuum at these incredible energies is not perfectly still. It is a seething foam of virtual particles flickering in and out of existence. Inflation takes these microscopic quantum fluctuations and stretches them to astronomical sizes, imprinting them onto the fabric of space-time. These minuscule ripples in density became the gravitational seeds for all future structure. Every galaxy, every star, every planet we see today grew from these tiny quantum jitters amplified by inflation. The detailed pattern of hot and cold spots we observe in the cosmic microwave background matches the predictions of inflationary theory with remarkable precision, providing a powerful, indirect confirmation that this wild event truly occurred. Yet for all its explanatory power, inflation itself is shrouded in mystery. What actually triggered it, what powered it, and why did it stop? The leading hypothesis involves a hypothetical field called the inflaton. Think of this as a kind of energy field that permeated the newborn cosmos, much like the Higgs field or the theorized quintessence field for dark energy. In this picture, the early universe found itself in a false vacuum state, a high-energy configuration that was temporarily stable but not in its true lowest energy state. This false vacuum possessed a peculiar property, a tremendous negative pressure that generated a powerful repulsive gravitational effect, driving the exponential expansion. As long as the inflaton field remained trapped in this false vacuum, inflation continued, stretching space at a ferocious rate. Eventually, however, the field tunneled or rolled down its energy landscape to its true vacuum state, a process called reheating. When this happened, the enormous energy stored in the inflaton field was dumped into the cosmos, flooding it with a hot soup of particles and radiation, effectively creating the hot Big Bang fireball we traditionally think of as the beginning. This moment set the initial conditions for the entire subsequent evolution of the universe. The nature of the inflaton field and the precise shape of its energy landscape are still completely unknown. Different theoretical models predict different outcomes. Was inflation a brief, single event, or did it occur in multiple stages? Could it be eternal, with some regions of space always inflating while others stop, giving birth to a vast multiverse? The specific inflationary model determines the statistical properties of the density fluctuations it produces, which in turn influences the large-scale structure of the universe we observe, the distribution of galaxy clusters, and the vast cosmic voids between them. While we have strong evidence that an inflationary event happened, we are still in the dark about its fundamental cause. Unlocking the physics of inflation would mean understanding the universe at energies 1 trillion times higher than what we can probe with our most powerful particle colliders. It is a window into the unification of gravity and quantum mechanics, a realm where the very concepts of space and time as we know them may have been born. This profound idea of a universe being stretched from a microscopic speck leads us to one of the most radical and mind-expanding concepts in all of science: the possibility that our entire cosmos is just one bubble in an infinite cosmic foam, part of a vast multiverse. The mechanism that makes this concept so compelling is a specific version of the inflationary theory we just explored, known as eternal inflation. In this picture, the process of inflation doesn't completely stop everywhere at once. Instead, the decay of the inflattened field from its high energy state is patchy. Think of a pot of water coming to a rolling boil. Most of the water is bubbling violently, but here and there, pockets of calm form as steam rises. In eternal inflation, the rapidly expanding space is like that violently bubbling water, the false vacuum where inflation continues at an exponential rate. But within this churning sea, random quantum fluctuations cause the inflattened field to drop to its lower energy state in localized regions. Each of these regions stops inflating and crystallizes into a stable, hot universe like our own, a single bubble in the greater, eternally inflating meta-universe. The key point is that the background space between these bubbles continues to inflate at a ferocious pace, pushing the baby universes far apart, ensuring they never collide or interact. And because the process is eternal, new bubbles are constantly being born, creating an endless, growing collection of separate universes, a multiverse. The staggering implication of this model is that each of these bubble universes could have emerged with different random properties. When a bubble forms, the way the inflattened field settles down can determine the fundamental laws and constants of physics within that bubble. This is because the energy of the field is ultimately converted into the particles and forces that define a universe. In one bubble, the strength of the electromagnetic force might be slightly stronger. In another, the mass of the electron could be different. Some universes might have 4 spatial dimensions instead of 3, or a different value for the cosmological constant. The multiverse, in this view, is not just a collection of copies of our universe with different historical outcomes. It is a vast landscape of realities where the very rules of the game are different. This provides a potential and deeply controversial answer to one of the most perplexing questions in physics. Why does our universe appear so finely tuned for life? Consider dark energy. The observed value of the cosmological constant is absurdly small, yet if it were even slightly larger, the universe would have expanded so rapidly that galaxies and stars could never have formed. If it were slightly more negative, the cosmos would have collapsed back on itself long ago. Through the lens of the multiverse, this fine-tuning isn't a miracle. It is a consequence of a cosmic selection effect, often called the anthropic principle. In an infinite array of universes with randomly varying constants, only in the rare ones where the numbers fall within a very narrow range can complex structures like galaxies, stars, planets, and ultimately, observers like us ever arise. We find ourselves in a universe with a certain expansion rate and a certain cosmological constant, not because those values are special or likely, but because they are the only ones that allow for our existence. We are, in a sense, cosmic lottery winners. This speculative framework forces us to confront profound questions about the nature of science itself. If the multiverse is real, and most universes are lifeless, barren voids or featureless soups of particles, then the laws we are trying to deduce may not be fundamental, universal laws at all. They may simply be the local bylaws of our particular cosmic neighborhood. The quest for a single, elegant theory of everything that explains all our constants would then be misguided, as those constants could be random, environmental outcomes. This is a deeply unsettling thought for many physicists, as it seems to move science from a framework of deterministic explanation to one of statistical chance. How can we test a theory that predicts an infinite number of unobservable universes? Proponents argue that the multiverse makes a testable prediction, that we should live in one of the rare universes capable of supporting life. The observed value of the cosmological constant, which seems so improbably fine-tuned, is actually evidence for the multiverse, as it fits the anthropic prediction perfectly. Skeptics, however, counter that this is not a prediction in the traditional sense, but a post hoc explanation that risks making cosmology untestable. The search continues for more concrete evidence, such as finding a specific imprint of our universe's bubble collision with another in the cosmic microwave background, or identifying a unique signature in the gravitational wave background from the violent era of reheating. For now, the multiverse remains a powerful, provocative consequence of our most successful theories of the early universe, a concept that stretches the imagination and challenges us to consider that our entire reality might be just a single page in an infinite cosmic library. While dark energy is the mysterious force pushing the cosmos apart, it is not the only major player in this cosmic tug-of-war. To understand the full picture of the universe's expansion, we must turn our attention to its silent, invisible partner, dark matter. This enigmatic substance makes up about 27% of the total energy budget of the cosmos, more than 5 times the amount of all the ordinary matter, the stars, planets, and everything we can see and touch combined. Yet, for all its abundance, we have never directly detected it. We cannot see it because it does not emit, absorb, or reflect any form of light or electromagnetic radiation. Its presence is revealed solely through its powerful gravitational influence, a ghostly tug that betrays its existence. We observe its effects in the way galaxies spin far too quickly to be held together only by the gravity of their visible stars, and in how massive clusters of galaxies bend the light from more distant objects, a phenomenon known as gravitational lensing. These cosmic fingerprints tell us that vast, invisible halos of dark matter envelop every galaxy, providing the gravitational scaffolding upon which the luminous universe is built. Without dark matter's immense gravitational pull, galaxies would have simply flown apart long ago, and the large-scale cosmic web of filaments and voids that structures our universe would never have formed. This foundational role in cosmic structure is its primary function, but its influence extends profoundly into the story of expansion itself. Dark matter acts as the universe's primary gravitational anchor, a cosmic brake constantly working against the repulsive push of dark energy. To visualize this cosmic struggle, picture the expansion of the universe as a grand race between two opposing teams. On one side, you have the relentless, outward driving force of dark energy. On the other, you have the collective gravitational pull of all matter, both dark and ordinary, constantly trying to rein the expansion back in. In the early universe, matter was the undisputed champion. The cosmos was much smaller and denser, and the gravitational attraction between all the concentrated matter was overwhelming. This caused the initial, explosive expansion from the Big Bang to slow down significantly for billions of years. Dark matter, making up the vast majority of this gravitating material, was the key ingredient in this braking effect. It provided the bulk of the gravitational glue that was trying to halt the cosmic rush and potentially pull everything back together. However, as the universe continued to expand, it also became more diffuse. The density of matter, both dark and ordinary, steadily decreased as it was spread out across an ever-increasing volume of space. Dark energy, in its most popular model as a cosmological constant, behaves differently. Its energy density remains constant. Think of it this way: as the universe grows, creating more cubic light-years of space, more dark energy appears to fill that new volume, maintaining a steady pressure. Around 5 to 6 billion years ago, a cosmic tipping point was reached. The density of matter had diluted enough that the constant, unyielding energy density of dark energy finally became dominant. From that moment on, the expansion of the universe stopped decelerating and began to accelerate, a transition we now observe through distant supernovae. So, while dark matter does not directly cause the acceleration, its behavior is absolutely critical to the story. The strength of its gravitational pull and the rate at which it diluted determine the precise moment in cosmic history when dark energy could take over the reins. This brings us to the profound, unresolved puzzle at the heart of dark matter. What is it actually made of? We know what it does, but we have no idea what it is. This is not just a trivial gap in our knowledge, it is a gaping hole that prevents us from fully understanding the expansion history of the cosmos. The standard model of cosmology makes very specific assumptions about dark matter, primarily that it is cold. This means its hypothetical particles moved slowly in the early universe, which allowed it to clump together easily and form the gravitational seeds for galaxies. This cold dark matter model, coupled with dark energy, forms our current standard model and has been incredibly successful at predicting the large-scale structure we observe. But what if dark matter is not perfectly cold and simple? What if it has properties we haven't accounted for? For instance, some theories propose that a fraction of dark matter might be warm, meaning its particles were moving at a significant fraction of the speed of light in the early universe. This would have a measurable effect. Warm dark matter would suppress the formation of small-scale structures, leading to fewer dwarf galaxies than our current models predict. This is a discrepancy that astronomers are actively investigating. If dark matter is warmer than we think, it would change how quickly structures formed in the early universe, which in turn would alter the timeline of when matter's gravitational dominance began to wane, subtly shifting the moment when dark energy took over. Another possibility is that dark matter is not completely inert. Perhaps it can interact with itself through some unknown force, or even occasionally with ordinary matter in ways more complex than just gravity. These self-interactions could change how dark matter clusters in the cores of galaxies, potentially SOLV, ING, Chinese letter, 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 Chinese letter. The density of dark matter in the centers of some galaxies appears less cusp-like than simulations predict. If dark matter has such complex interactions, its distribution throughout cosmic history would be different, and therefore its gravitational braking power would have evolved differently. This means that the unknown nature of dark matter is not a separate mystery from the expansion of the universe. The two are inextricably linked. The precise way in which the cosmic expansion changed from deceleration to acceleration is a sensitive probe of the properties of both dark energy and dark matter. By measuring the expansion history with ever greater precision, we are not only learning about the force pushing the universe apart, but we are also conducting a grand, indirect experiment on the nature of the invisible matter that forms its cosmic skeleton. Unlocking the identity of dark matter is therefore essential for completing our understanding of the universe's past, present, and future expansion. It is the silent, dominant gravitational partner in a dance with a mysterious repulsive force, and we are only just beginning to hear the music. For over a century, Einstein's theory of general relativity has stood as a pillar of modern physics, a masterpiece of human intellect that has passed every test with flying colors. It perfectly predicts the orbit of Mercury, explains the bending of starlight around the sun, and is so precise that it's essential for the GPS in your phone to function correctly. But as we turn our gaze from our solar system to the cosmos at large, a provocative question emerges. Could this celebrated theory, for all its local successes, be incomplete when applied to the vast, sprawling scales of the entire universe? Is it possible that the phenomenon we call dark energy is not a mysterious substance at all, but rather a sign that our understanding of gravity itself needs a fundamental revision on the grandest stages? This is not a question asked lightly, but one forced upon us by the perplexing inconsistencies between our observations and our predictions. The core of general relativity is a beautiful, if complex, idea. that matter and energy tell spacetime how to curve, and that curved spacetime, in turn, tells matter and energy how to move. This curvature is what we experience as gravity. For the solar system, for black holes, for binary pulsars, this geometric picture works flawlessly. But when we apply these same equations to the universe as a whole, and we input all the matter and energy we know exists, the equations predict that the cosmic expansion should be slowing down. The observed acceleration, therefore, presents a stark either-or dilemma. Either the universe contains a previously unknown dominant component, dark energy, that produces a repulsive gravitational effect, or our equations for gravity, the very rules of the cosmic game, are subtly wrong on distances spanning billions of light years. The majority of physicists have taken the first path, embarking on the quest for dark energy, but a small, dedicated group of researchers are exploring the second, more radical possibility. They are developing and testing alternative theories of gravity, frameworks that attempt to explain the cosmic acceleration and other galactic mysteries without invoking the enigmatic dark energy. The most prominent of these alternatives is known as modified Newtonian dynamics, or MUND. Originally proposed in the 1980s by physicist Mordechai Milgrom, MUND was not designed to explain cosmic expansion, but to solve a separate puzzle, the rotation curves of galaxies. Just as dark matter was invoked to explain why galaxies spin too fast, MUND offers a different solution. It suggests that Newton's laws of motion, and by extension Einstein's theory, require a tiny modification when the gravitational acceleration becomes incredibly weak, which happens in the outer suburbs of galaxies and in the vast emptiness between galaxy clusters. Milgrom proposed a new constant of nature, a specific, minuscule acceleration threshold. Above this threshold, gravity behaves exactly as Newton and Einstein predicted. But below it, in the realm of extremely weak forces, gravity becomes stronger than expected. This single tweak successfully explains the flat rotation curves of countless galaxies without needing any invisible dark matter halo. For its original purpose, MUND has been surprisingly effective, often matching galactic observations more precisely than the standard dark matter model. When physicists began to construct fully relativistic versions of MUND theories that could be applied to the entire cosmos, not just individual galaxies, they found something astonishing. Some of these theories naturally predict an accelerated expansion of the universe, the same modification that strengthens gravity on galactic scales to mimic dark matter can, in the context of the full universe, produce a repulsive effect that mimics dark energy. In this picture, there is no mysterious substance making up 68% of the cosmos. There is only a slight adjustment to the laws of gravity that becomes significant on both galactic and cosmic scales. This offers an incredibly elegant unification. One single modification could potentially explain two of the greatest mysteries in astrophysics: the missing mass in galaxies and the accelerated expansion, without needing two separate, undiscovered components. However, this elegant idea faces immense challenges. The primary hurdle is that MUND and its relativistic cousins have a very difficult time explaining all the evidence for dark matter on larger scales. While it works wonderfully for individual galaxies, it struggles to account for the gravitational lensing effects observed in massive clusters of galaxies, where the bending of light is far too strong to be explained by the visible matter alone, even with MUND modifications. Proponents of modified gravity have to propose new forms of matter anyway, often called hot dark matter or other exotic fields, to make their models work, which to many critics seems to defeat the original simplicity of the proposal. Furthermore, the Bullet Cluster, a famous pair of colliding galaxy clusters, provides a powerful piece of evidence for the dark matter paradigm. In this system, the visible gas clouds collide and slow down, but the majority of the mass, as mapped by gravitational lensing, appears to have sailed right through the collision, separated from the normal matter. This is exactly what a collision of two clouds of collisionless dark matter would look like, but it is very difficult for a modified gravity theory to explain why the gravitational field would be strongest where there is the least visible matter. Beyond MAND, there is a whole zoo of other modified gravity theories with names like F of R gravity, brainworld scenarios, and tensor vector scalar gravity. Each one attempts to tweak Einstein's equations in a different way, often by adding new fields or extra dimensions that alter the behavior of gravity on cosmic scales. The goal of all these theories is the same: to produce a universe that accelerates without dark energy. The ongoing battle between these two paradigms, dark energy versus modified gravity, is not just a philosophical debate. It is a driving force behind some of the most ambitious astronomical projects of our time. The key to distinguishing between them lies in making extremely precise measurements of how cosmic structures grow over time. In a universe dominated by a cosmological constant, the accelerated expansion suppresses the formation of new galaxy clusters. Gravity becomes less effective at pulling matter together because the repulsive push of dark energy is constantly driving it apart. In a modified gravity scenario, the accelerated expansion is tied to the way gravity works, and this can lead to a different rate of structure formation. Upcoming observatories like the Vera C, Rubin Observatory, and the Euclid Space Telescope are designed to map billions of galaxies and trace the dark matter scaffolding of the universe with unprecedented detail. They will measure the cosmic growth history so precisely that any deviation from the predictions of general relativity coupled with dark energy could be a smoking gun for a new theory of gravity. The question of whether Einstein was ultimately right on all scales is one of the most profound in modern science. To discover that general relativity fails on cosmic horizons would be a revolution on par with the transition from Newtonian mechanics to relativity itself. It would mean that the force that governs the fall of an apple and the orbit of a planet is not the final word on the grandest cosmic stage, and that our universe operates by a deeper, more complex set of rules than we ever imagined. At the heart of this entire cosmic drama, the expansion, the acceleration, the very structure of reality, lies a stage we have been taking for granted: space-time itself. We've been talking about it as if it were a smooth, continuous fabric, a blank canvas upon which the universe is painted. But what if this canvas is not fundamental? What if, when we peer down to the very smallest possible scales, the smooth fabric of space and time dissolves into a seething, chaotic foam, a digital pixelation of reality itself? This isn't just a philosophical curiosity. It is perhaps the most urgent frontier in fundamental physics, and it holds the key to understanding the universe's expansion in its very first instance, a regime where our current laws of physics completely break down. The problem is a clash of titans. On one hand, we have Einstein's theory of general relativity, which describes gravity as the elegant curvature of a smooth, continuous space-time continuum. It is a theory of the very large, the cosmic scale, and it works spectacularly well. On the other hand, we have quantum mechanics, the rulebook for the atomic and subatomic world. It is a theory of probabilities, discrete packets of energy, and fundamental uncertainty. It, too, works flawlessly within its domain. The catastrophic issue is that these two pillars of modern physics are utterly incompatible. They speak different mathematical languages and make contradictory claims about the nature of reality. This conflict becomes violent in extreme environments where both immense gravity and tiny quantum scales are relevant places, like the central singularity of a black hole or the very first moment of the Big Bang. In that initial, inconceivably hot and dense state, the universe was smaller than a single atom. To understand its birth and its initial explosive expansion, we need a theory that can marry gravity with quantum mechanics. We need a theory of quantum gravity. The current leading candidate for such a theory is string theory. It proposes a breathtakingly elegant solution. The fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy strings. Just as a single violin string can vibrate at different frequencies to produce different musical notes, these fundamental strings vibrate in different modes, and each distinct vibration corresponds to a different fundamental particle. An electron is one vibrational pattern, a quark is another, the photon, carrier of light, is yet another. Crucially, one of these vibrational patterns perfectly describes the graviton, the hypothetical quantum particle that would mediate the force of gravity. In one stroke, string theory seems to unify all forces and all matter. But this elegance comes at a cost. The mathematics of string theory only works consistently if the universe has more than the three spatial dimensions and one time dimension we experience. It requires extra dimensions curled up into shapes so small that we cannot perceive them. This is not as outlandish as it sounds. Imagine a garden hose stretching far into the distance. From a distance, it looks like a simple one-dimensional line. But if an ant crawls on it, the ant can move along its length, but also around its circular cross-section. The hose has a long, extended dimension and a tiny, compact, curled-up dimension. String theory suggests our universe is like that, but with 6 or 7 extra curled-up dimensions at every single point in space. The properties of these hidden dimensions would determine the laws of physics in our visible universe, including the strength of gravity and potentially the value of the cosmological constant. This provides a potential, if highly speculative, pathway to understanding why our universe has the specific expansion properties it does. The other major approach to quantum gravity is loop quantum gravity. It takes a very different path. Instead of proposing new fundamental objects like strings, it tries to quantize space and time themselves directly, applying the principles of quantum mechanics to the geometry of space-time. In this theory, space is not smooth and continuous. It is composed of discrete, indivisible atoms of space. Picture the fabric of the cosmos not as a smooth silk sheet, but as a chainmail tunic woven from a finite number of tiny, interwoven loops. These loops form a network, a spin foam, and the volume and area of space come in tiny, discrete packets. There is a smallest possible volume, a smallest possible area. Time, too, is not a continuous flow, but progresses in discrete, tiny ticks of a fundamental clock. This has a profound implication for the Big Bang. In general relativity, the Big Bang is a true singularity, a point of infinite density and temperature where the laws of physics cease to exist. But in loop quantum gravity, because there is a smallest possible volume, matter and energy cannot be compressed into an infinitely small point. Instead, the theory suggests that a previous universe could have collapsed, but when it reached this maximum possible density, a quantum repulsive force would have kicked in, causing a big bounce, a rebound into a new expanding universe. In this view, the Big Bang was not a beginning, but a transition from a prior cosmic phase. This radically alters our conception of the initial expansion, suggesting it was not a singular creation from nothing, but part of an eternal cycle. Both of these approaches point toward a concept that is reshaping modern physics. The idea that space-time is not fundamental but emergent, just as the property of temperature emerges from the chaotic jostling of countless molecules and is not a property of any single molecule. Smooth, continuous space-time may emerge from the collective behavior of something more basic. In string theory, space-time may emerge from the interactions of strings. In other approaches, like the holographic principle, our three-dimensional reality might be a projection of information encoded on a two-dimensional surface surrounding us, much like a three-dimensional hologram emerges from a flat, two-dimensional film. This suggests that the expansion of the universe might not be the stretching of a fundamental fabric, but rather the evolution of an underlying quantum system, a vast cosmic computer processing information. A successful theory of quantum gravity would not just tell us what happened at the Big Bang. It would revolutionize our understanding of dark energy and the cosmological constant. Is the acceleration of the universe driven by a substance, or is it a consequence of the way space-time emerges from its quantum constituents? Could the value of the cosmological constant be a result of the specific way our universe's quantum bits are entangled? We are, for now, grappling in the dark, trying to understand the engine of the cosmos without knowing what the engine is made of. The nature of space-time itself is the deepest mystery, the foundation upon which all our other questions are built. Until we solve it, our picture of the expanding universe from its first moment to its ultimate fate remains profoundly incomplete. This relentless march backward through cosmic history, past the formation of galaxies, past the first stars, past the release of the cosmic microwave background, brings us to the ultimate precipice of knowledge, a moment shrouded in the deepest mystery. What or who lit the fuse for the Big Bang? We have traced the expansion of the universe back to an infinitesimal point of infinite density and temperature, a singularity where the known laws of physics completely break down. To ask what happened before this moment seems, at first, like a nonsensical question, akin to asking what is north of the North Pole. In the framework of classical general relativity, the Big Bang is the absolute beginning, not just of matter and energy, but of space and time themselves. There is no before, because time itself was created in that cataclysmic event. Yet, the human mind naturally rebels against this idea of a true beginning from nothing, pushing us to formulate theories that might allow us to peer beyond the veil of that initial singularity. One of the most profound and mind-bending attempts to address this comes from the work of James Hartle and Stephen Hawking, known as the no-boundary proposal. Imagine the entirety of cosmic history as the surface of the Earth. The Big Bang singularity is like the North Pole. If you ask what is north of the North Pole, the question has no meaning, it is the boundary. But in the Hartle-Hawking proposal, the universe is like the surface of the Earth with the North Pole smoothly rounded off. There is no sharp, singular boundary. In this model, the dimension of time, as we approach the beginning, behaves less like a line and more like a direction in space. In the extreme early universe, time becomes imaginary, a mathematical trick that allows for a smooth, finite, and completely self-contained origin. The universe would have no edge in space or time. It would simply be. It wouldn't explode into anything because there was no pre-existing space. It wouldn't begin at a time because time as we know it would only emerge as the universe cooled and expanded. In this vision, the question, what happened before the Big Bang, is rendered obsolete because the universe has no beginning, only a finite but unbounded origin, much like the surface of a sphere has no edge. This elegant idea removes the need for a supernatural creator or an uncaused cause, suggesting the universe could be entirely self-contained, a cosmic bubble of its own making. A radically different, yet equally compelling, vision is the concept of the cyclic universe, which directly challenges the notion of a unique beginning. In this ancient idea, reinvigorated by modern physics, the Big Bang was not the start of everything, but merely the latest in an endless series of cosmic cycles. One sophisticated version of this is the ekpyrotic model, born from string theory. It proposes our three-dimensional universe exists on a membrane or brain, floating in a higher dimensional space. The Big Bang in this picture could have been the result of a collision between our brain and a neighboring one. The immense energy of this collision would have heated our universe to incredible temperatures, setting off the expansion we see today, but it wouldn't have been a true beginning. Before the collision, both brains existed, possibly undergoing their own cycles of approach and separation. Another cyclic model, conformal cyclic cosmology, proposed by Roger Penrose, suggests an even more breathtaking possibility, that the universe's future infinity becomes the next universe's Big Bang. In the far, far future, after black holes have evaporated and particles have lost all their mass, the universe becomes a vast, empty, and featureless sea of radiation. In this state, Penrose argues, it loses all sense of scale. It becomes conformally invariant. This smooth, cold, infinite emptiness is mathematically identical to the hot, dense, small singularity of a new Big Bang. The end of one eon becomes the beginning of the next in an endless chain, with information from the previous cycle potentially imprinted as faint, circular patterns in the cosmic microwave background of the next. Then there is the staggering implication of eternal inflation, which we touched upon with the multiverse. If inflation is truly eternal, then the Big Bang that created our observable universe was not a unique, one-time event. It was merely a local bubble nucleation in an eternally inflating meta-universe. In this grander picture, the question, what caused the Big Bang, is like asking what caused a particular bubble to form in a pot of boiling water. The larger system, the eternally inflating false vacuum, has always existed, and within it, countless Big Bangs are constantly occurring, each giving birth to its own separate universe with potentially different physical laws. Our entire cosmic history is just one incident in an infinite, ongoing process that has no beginning and no end. Each of these theories offers a different answer to the ultimate origin, but they all share a common thread. They push the concept of a beginning into deeper, more abstract territory. The Hartle-Hawking proposal removes the singular beginning by blending time and space. The cyclic models remove it by postulating an endless cycle. The multiverse removes it by suggesting our beginning was merely a local event in a much older, perhaps eternal, meta-reality. What they force us to confront is that our common-sense notion of cause and effect, which operates so well within our universe, may completely fail when applied to the universe as a whole. The search for a first cause may be a logical error, a misapplication of the rules of the game to the game board itself. The mystery of what caused the Big Bang, therefore, stands as the final frontier of cosmology, a question that probes not only the limits of our telescopes and equations, but the very limits of human understanding and the nature of existence itself. This brings us to a question that strikes at the very bedrock of physics itself. Are the rules of the game truly fixed? For centuries, science has operated on the assumption that the fundamental constants of nature are just that, constant. The speed of light, the strength of gravity, the charge of an electron, these are the immutable numbers that plug into our equations, the settings on the cosmic control panel that make our universe what it is. But what if we've been wrong? What if these constants are more like dials that have been slowly turning over the lifetime of the cosmos? It's a startling possibility, and if true, it would force us to rewrite not only our physics textbooks but also our entire understanding of the universe's expansion history. Consider the fine structure constant, often denoted by the Greek letter alpha. This isn't a single force, but a magical number that governs the strength of the electromagnetic interaction. It determines how tightly atoms hold onto their electrons, the energy levels within every element, and the very nature of the chemical bonds that build our world. If the fine structure constant were even a few % different, the delicate balance of nuclear fusion in stars would be thrown into chaos. Carbon might not form, and the complex chemistry necessary for life could become impossible. For a long time, we assumed this number was locked in place. Then, about 2 decades ago, a team of astronomers led by John Webb began analyzing the light from incredibly distant quasars. These brilliant beacons are the cores of active galaxies, and their light travels for billions of years before reaching us, passing through interstellar gas clouds that imprint specific absorption lines on the spectrum, a kind of cosmic barcode. By studying the spacing of these lines, Webb's team could effectively measure the value of the fine structure constant in the distant past. To their astonishment, they found evidence that it might have been slightly different billions of years ago. The data suggested that in certain directions of the sky, alpha was once minutely smaller. This wasn't a huge change, just a few parts in a million, but in the world of precision physics, it was seismic. The implications are staggering. If the electromagnetic force was weaker in the past, it would mean that atoms behaved differently. The energy released in nuclear reactions would have been altered, which in turn would have affected the life cycle of the first stars and the creation of heavy elements. This single tiny dial could have reshaped the entire cosmic story of how galaxies lit up and evolved, but the potential for variation doesn't stop there. An even more profound candidate for change is the strength of gravity itself. In our current models, the expansion rate of the universe is a delicate dance between the attractive pull of gravity and the repulsive push of dark energy. Gravity's strength is set by Newton's gravitational constant, big G. What if big G has not always been so big? If gravity was stronger in the early universe, it would have increased the rate at which matter clumped together, accelerating the formation of the first stars and galaxies. A stronger gravitational pull in the past would also have meant a more powerful brake on cosmic expansion. This could fundamentally alter our interpretation of the supernova data that revealed dark energy. Perhaps the universe isn't being pushed apart by a mysterious force, but was instead held back more strongly in its youth by a gravity that has since weakened. The observed acceleration could, in this radical picture, be an illusion created by a gravitational constant that is slowly decaying over cosmic time. The mechanisms that could allow for such changes are deeply tied to some of the most ambitious theories in physics. In string theory, for instance, the fundamental constants are not primary numbers but are determined by the geometry of the extra compactified dimensions. If those hidden dimensions were to slowly evolve or shift their shape over billions of years, the constants we measure in our three-dimensional world would shift with them. The cosmological constant, which we attribute to dark energy, could itself be the manifestation of a field that is dynamically settling into its minimum value, causing what we perceive as constants to gradually change as it relaxes. This idea connects directly back to quintessence models, where a dynamic field could influence both the expansion rate and the fundamental couplings of particle physics in an interconnected cosmic evolution. So how do we test such a mind-bending concept? Astronomers are turning the universe into a giant laboratory, using the most distant objects as time machines. They are scrutinizing the spectra of ancient quasars with increasingly powerful telescopes, like the extremely large telescope being built in Chile, to see if the fine structure constant or the proton-to-electron mass ratio show any definitive sign of drift. They are also looking at the cosmic microwave background. The precise pattern of fluctuations in this ancient light is exquisitely sensitive to the physics of the early universe, including the values of the fundamental constants at that time. Any deviation from the predicted pattern could be a fingerprint of inconstant constants. Furthermore, precise measurements of the orbits of planets in our solar system over decades, and even the timing of millisecond pulsars, provide a local, modern test for any slow drift in the strength of gravity. The fact that we have not yet found conclusive, universally accepted evidence for varying constants makes this one of the most tantalizing frontiers in cosmology. It sits in a precarious balance, a hypothesis that is neither proven nor ruled out. The possibility that the universe's rulebook is a living document, subtly changing over eons, challenges our most deeply held assumptions about the nature of reality. If the constants are not fixed, then the universe is not a static arena with fixed laws, but a dynamic entity whose very laws are part of its evolutionary story. Unraveling this mystery would not just explain the past, it would reveal whether the cosmos we see today is the permanent state of things, or merely a single frame in a much longer, more evolving cosmic film. To grasp the monumental structures that fill our cosmos, from the grand tapestry of galaxy clusters to the vast, empty voids between them, we must shrink our perspective down to the most fundamental level imaginable, to a realm governed by chaos and chance. The origin of everything we see can be traced back to a phenomenon that seems almost insignificant: quantum fluctuations. In the frantic energy of the universe's first fraction of a second, empty space was not truly empty. Borrowing from the bizarre rules of quantum mechanics, pairs of virtual particles and antiparticles continuously flickered into and out of existence, a seething, foamy sea of creation and annihilation happening over distances trillions of times smaller than an atom. These were not imperfections, they were the very nature of reality at its smallest scale, a fundamental uncertainty woven into the fabric of existence. For the briefest moment, these quantum jitters were trivial, microscopic ripples that appeared and vanished almost instantaneously, but then inflation struck. That period of hyper-expansion acted like a cosmic amplifier of unimaginable power. As space-time stretched at a rate faster than light, it did not smooth out these tiny fluctuations. Instead, it grabbed them and stretched them across the cosmos, locking them in place and magnifying them from the quantum realm to the astronomical scale. The microscopic randomness of the quantum vacuum was imprinted onto the density of the universe, creating regions that were ever so slightly denser than average, and others that were ever so slightly more sparse. This is the breathtaking connection. The largest structures in the universe owe their existence to the smallest possible events. After inflation ended and the universe filled with a hot plasma, gravity got to work on these initial seeds. The slightly denser patches had a tiny bit more gravitational pull, slowly drawing in more and more matter from their surroundings over hundreds of millions of years. The slightly sparser patches, conversely, were emptied out as matter flowed away from them. The delicate patterns we now see in the cosmic microwave background, the hot and cold spots that map the early universe, are the direct fossilized imprint of those amplified quantum fluctuations. They are the blueprints from which every galaxy, every star, and every cosmic filament would eventually be built. Without this initial, quantum-induced lumpiness, the universe would have remained a perfectly smooth, dull, and featureless soup of particles, and we would not be here to observe it. But this profound link between the quantum world and cosmic structure leads to an even more speculative and tantalizing question. Could similar quantum processes be at work right now, influencing the expansion dynamics of the universe itself? We've already encountered the cosmological constant problem, where the quantum calculation of vacuum energy is catastrophically larger than what we observe. This suggests that our understanding of the quantum vacuum is fundamentally flawed. The vacuum of space is not a true nothing. According to quantum field theory, it is a hive of activity, with fields constantly undergoing fluctuations that endow empty space with a fundamental energy. If this vacuum energy were as large as the raw math suggests, its repulsive gravity would have torn the universe apart instantly. The fact that it didn't, and that we instead measure a small, positive value for dark energy, is the central puzzle. This has led some theorists to propose that dark energy itself might be a manifestation of a dynamical quantum process. Perhaps the vacuum energy is not a fixed number, but the result of a complex balancing act, a cancellation of enormous positive and negative contributions from different quantum fields that almost but not perfectly cancel out, leaving behind the tiny residual we call dark energy. Another, even more radical idea suggests that the very expansion of the universe could be driven by a continuous process of quantum creation. In one speculative model, the universe is constantly undergoing the quantum birth of new spacetime atoms at a microscopic level, a process that, when averaged over the vastness of the cosmos, manifests as the smooth expansion we measure. It's a concept that challenges our classical intuition, proposing that the large-scale evolution of the universe is not governed by a simple set of equations, but emerges from the collective, statistical behavior of countless underlying quantum events, much like the pressure of a gas emerges from the chaotic motion of its molecules. While these ideas are highly speculative and far from being proven, They highlight a critical frontier in modern physics. We have successfully connected quantum fluctuations to the structure within the universe, but we have yet to fully understand if quantum mechanics also governs the evolution of the universe, the very stretching of the space-time stage upon which the cosmic drama plays out. Unraveling this deeper connection may be the key to finally reconciling the physics of the very small with the destiny of the very large, revealing a universe that is quantum to its very core. Now we arrive at a question that bridges the physics of the unimaginably small with the destiny of the entire cosmos, a deep puzzle that asks whether the universe is fundamentally forgetful. Is the universe losing information? This might sound like an abstract philosophical query, but it's a concrete and urgent problem that pits quantum mechanics against gravity, and its resolution could redefine our understanding of reality in an accelerating cosmos. The heart of this mystery begins with black holes, the ultimate cosmic shredders. According to Einstein's general relativity, a black hole is defined only by its mass, electric charge, and spin. If you throw a grand piano, a library of encyclopedias, or a collection of priceless artifacts into a black hole, the theory suggests the black hole would respond identically. It would simply get more massive and slightly larger. All the unique, intricate information about what fell in the grain of the piano's wood, the words in the books, the atomic structure of the artifacts, seems to be completely and permanently erased from our universe. The problem is, quantum mechanics holds a sacred foundational law. Information is never truly lost. It can be scrambled, transformed, or hidden, but it must, in principle, be recoverable. This fundamental conflict is the famous black hole information paradox, sharpened by Stephen Hawking's discovery that black holes aren't entirely black. They slowly evaporate by emitting a faint glow of particles, now known as Hawking radiation. Hawking's original calculations showed that this radiation is purely thermal, like the heat from a stove. It contains no specific information about what fell into the black hole. So, if a black hole eventually evaporates completely, leaving behind nothing but this random thermal radiation, then the information about everything it ever consumed is utterly gone, violating a core tenet of quantum theory. This paradox has driven physicists to the brink for decades. The potential resolution, which has gained significant traction, involves the black hole's event horizon acting not as a destructive firewall, but as an incredibly complex scrambler of quantum information. The idea is that the information about infalling matter isn't destroyed. It's imprinted onto the event horizon itself in a scrambled, two-dimensional hologram. Then, as the black hole emits Hawking radiation, this information is slowly and chaotically encoded back into that radiation. It's like burning a book. To all appearances, the information is lost in the smoke and ash, but in principle, if you could collect every particle of smoke and every speck of ash and analyze them with infinite precision, you could reconstruct the book. The information was never gone, just transformed into an astronomically complex form. This holographic principle suggests that all the information describing a three-dimensional volume of space can be encoded on its two-dimensional boundary, a revolutionary idea that profoundly links information to the very fabric of space-time. But this intricate dance of information preservation worked out for black holes now faces an even grander and more ominous challenge: the accelerating expansion of our entire universe. Driven by dark energy, our cosmos is not only expanding but speeding up, and this creates a cosmic horizon much like a black hole's event horizon. This is not a boundary in space but a limit in time. Because the universe is expanding faster than light can travel across the vast distances between galaxy clusters, there is a fundamental limit to what we can ever see or interact with. Light from galaxies beyond this horizon will never, ever reach us. As the acceleration continues, this horizon will shrink around us, and more of the cosmos will permanently disappear from our view. This presents a cosmological version of the information paradox. Imagine a quantum particle or an entire galaxy crossing over this cosmic event horizon. From our perspective inside the horizon, that object isn't torn apart. It just becomes forever invisible, its light infinitely redshifted until it fades from existence. The question is, what happens to the quantum information it carried? In the standard picture of quantum field theory in an accelerating universe, that information is effectively lost to us, just as information seemed lost in Hawking's original black hole calculation. The vacuum state of the universe in the presence of a cosmic horizon is a thermal state filled with a faint, uniform glow called the Gibbons-Hawking radiation, analogous to Hawking radiation. If this is the final word, then the accelerating expansion of the universe acts as a perpetual, low-temperature information eraser. As more and more of the cosmos vanishes beyond the horizon, the quantum information associated with those regions becomes fundamentally inaccessible, posing a direct threat to the unitarity of quantum mechanics, the principle that the evolution of the universe must be predictable and information-preserving. This leads to a terrifying possibility known as the cosmic death by irreversibility. In this scenario, the universe doesn't end in fire or ice, but in a fundamental loss of quantum coherence. The orderly, deterministic evolution mandated by quantum mechanics could break down on a cosmic scale due to the relentless expansion. Some physicists argue for a way out, suggesting that the holographic principle must apply to the cosmic horizon as well. Perhaps the entire observable universe can be described as a hologram on its bounding surface, and information that crosses the horizon isn't lost but is encoded on that surface. Yet, this is profoundly more complex than the black hole case because our cosmic horizon is not static. It's dynamically evolving, and we are inside the system. The ultimate fate of information in an eternally expanding universe remains one of the most profound and unsettling open questions. It forces us to ask whether the laws of quantum mechanics forged in the laboratories of Earth are truly universal and eternal, or if they themselves might break down in the face of the cosmos's ultimate expansion, leading to a future where the universe not only grows cold and dark, but also forgets its own past. As we contemplate the quantum origins of cosmic structure, we are drawn to consider another class of hypothetical relics that could have been forged in the same fiery forge of the early universe, remnants so strange and massive they would warp the very fabric of spacetime itself. These are topological defects, and they arise not from quantum jitters but from a different kind of cosmic trauma, phase transitions in the fundamental fields that permeate reality. To grasp this, imagine the universe cooling from its unimaginably hot birth, much like water freezing into ice. As liquid water cools, its molecules must suddenly lock into a rigid, crystalline structure. But this process isn't always perfect. Different regions of the water might start freezing independently, and when their growing ice crystals meet, they often don't align perfectly. The mismatch creates a flaw in the crystal lattice, a crack or a dislocation that is frozen into the final structure. The early universe underwent similar but far more dramatic phase transitions. As it expanded and cooled, the unified forces of nature, thought to be one superforce at the highest energies, began to split apart. The strong nuclear force separated from the electroweak force, and later, the electromagnetic and weak forces went their separate ways. Each of these splits was a cosmic version of water freezing, a moment when the underlying quantum fields had to choose a new stable state, or what physicists call a vacuum state. The critical point is that there was often more than one possible stable state for the field to settle into. Much like water molecules can form ice crystals oriented in many different directions. Different regions of the universe, separated by distances greater than light could have traveled, would have made their choices independently. When these cosmic domains eventually met, the mismatch between their chosen field configurations could not always be smoothed out. This irreconcilable difference became permanently locked into the fabric of spacetime, creating a topological defect. These defects are classified by their dimensionality, and they form a zoo of exotic entities. The most famous and potentially long-lived of these are cosmic strings. Think of a cosmic string not as a string made of atoms, but as a flaw in spacetime, an incredibly thin, filament-like region where the fundamental fields are trapped in a high-energy state. They are not strings in space, they are space, or rather, a defect in its structure. Their properties are mind-boggling. A cosmic string would be thinner than a proton, yet a single inch of it could weigh as much as a mountain range. This immense mass density gives it a gravitational pull so strong that it would act as a ripple in spacetime, a gravitational lens that can distort the light from galaxies behind it. Even more bizarrely, the geometry around a cosmic string is so peculiar that if you were to travel in a perfect circle around one, you would find that the total angles of your journey would not add up to 360 degrees. Space itself would have a deficit angle, creating a double image effect where an astronomer could see the same galaxy in two different places in the sky. Then there are other, even more extreme defects. Domain walls are two-dimensional sheets that separate entire regions of the universe where the fields settled into different vacuum states. A domain wall would be a gravitational nightmare, a sheet of energy so dense that it would violently pull matter toward it, effectively carving the universe into distinct territories. Fortunately, most theories suggest that domain walls would be so catastrophically disruptive to the cosmos that their existence is heavily constrained. If they were common, we would see their dramatic imprint everywhere, which we do not. Textures are more ephemeral, three-dimensional knots of energy that are unstable and would likely have unraveled in the very early universe, but cosmic strings, if they were created and stable, could have persisted to the present day, drifting through the cosmos like ghostly filaments from the dawn of time. The connection to cosmic expansion is profound. The formation of these defects is intimately tied to the physics of inflation. In fact, one of the great successes of inflationary theory is that it typically predicts a universe so smooth and flat that it should be largely free of these dangerous defects. Inflation would have stretched any initial defects to such immense scales or diluted them away that they become irrelevant. Therefore, the non-observation of topological defects is actually a piece of evidence in favor of inflation. However, some more complex inflationary models do allow for the production of certain types of strings that could have formed after or at the very end of inflation. If such strings exist, their gravitational influence could have played a role in the early universe's expansion dynamics. A network of cosmic strings crisscrossing the cosmos would have contributed a different form of energy density to the universe. Unlike matter or radiation, which dilute as the universe expands, a network of strings would scale in a way that could have subtly influenced the transition between different eras of cosmic expansion. Furthermore, these strings would not have been static. They would have wriggled and vibrated at relativistic speeds, and when two strings crossed, they could have severed and reconnected, sending off ripples in spacetime known as gravitational waves. A cosmic string network would thus be a persistent source of a stochastic gravitational wave background, a low hum from the early universe that might be detectable by future observatories like the Laser Interferometer Space Antenna, or LISA. This provides a direct observational pathway to hunt for these phantom-like structures. The most promising place to look for their imprint, however, remains the cosmic microwave background. The immense gravity of a cosmic string would have affected the path of the ancient light traveling toward us. A string moving between us and the CMB would create a very specific, sharp discontinuity in the temperature of the background radiation, a step-like change where one side is slightly hotter than the other. Astronomers have scoured the Planck satellite data for such signatures, and while no definitive evidence has been found, the search has placed stringent limits on the possible density and properties of any cosmic string network. The hunt for topological defects is thus a double-edged sword. Finding one would be a monumental discovery, providing direct, tangible evidence for the grand unified theories of particle physics and revealing a new chapter about the universe's violent infancy. It would show us that the cosmos is not only expanding but is also textured with ancient scars from its formative moments. Their continued non-detection, however, powerfully reinforces our current cosmological model and helps us narrow down the vast landscape of possible theories about the universe's very first moments. But this underlying uniformity itself presents one of the most stubborn puzzles in cosmology, a problem so fundamental that it forces us to confront the very limits of the classic Big Bang model. It's known as the horizon problem, and it asks a seemingly simple question. Why is the universe so incredibly smooth? When we look out into space, we find that the temperature of the cosmic microwave background is the same in every direction to within a tiny fraction of a degree. Two regions on opposite sides of the sky, billions of light years apart, have somehow settled into an almost perfect thermal equilibrium, as if they had once been in intimate contact, sharing heat to reach a common temperature. And this is the core of the paradox. According to the standard Big Bang timeline, without any extra ingredients, those two regions have never been in causal contact. Let's break that down. The universe has a finite age, about 13.8 billion years, and nothing can travel faster than light. This means there is a maximum distance over which any 2 points could have ever communicated, a cosmic horizon. When we look at the CMB, we are seeing light that was emitted when the universe was just 380,000 years old. At that time, the distance between 2 points on opposite sides of our sky was far greater than the distance that light could have traveled since the beginning of the universe. They were outside each other's horizons, completely disconnected from one another. It would be like having 2 cups of coffee, one in Paris and one in Tokyo, that spontaneously cool to the exact same temperature down to 1,000th of a degree without any connection between them. It's a coordination act of breathtaking precision across an impossibly vast stage, and the classic Big Bang model has no explanation for how it was achieved. This smoothness isn't just a curious detail, it is a foundational characteristic of our cosmos, and its explanation is one of the strongest arguments for a dramatic addition to our cosmic story, the theory of inflation. Inflation solves the horizon problem by fundamentally rewriting the early universe's timeline. It proposes that before the universe was even a tiny fraction of a second old, it underwent a period of hyper-expansion, ballooning in size by a factor of at least 10 to the 26 in a span of time as short as 10 to the negative 36 seconds. This changes everything. In the pre-inflationary universe, the entire volume that would become our observable cosmos was an unimaginably small subatomic speck. And crucially, this tiny region was small enough for every part of it to be in causal contact. Light signals could zip across it countless times, allowing it to mix thoroughly and reach a perfectly uniform temperature, just like a single, well-stirred cup of coffee. Then inflation acted. It took this tiny, smooth, and thermally equilibrated patch and stretched it to a size larger than our entire observable universe today. The magnificent uniformity we see in the CMB is simply the inherited uniformity of that initial, minuscule seed, stretched to a cosmic scale. The regions that now appear on opposite sides of the sky were once cozy neighbors, able to exchange energy and information freely before being flung apart by the inflationary surge. It's an elegant and powerful solution, but it immediately raises the next deeper question. If inflation is the answer, what is the definitive, proven mechanism that drove it? We have a compelling theoretical framework, but we lack the smoking gun that tells us precisely how it happened. The leading hypothesis involves a hypothetical field called the inflaton. Think of this as a kind of energy field that temporarily possessed a peculiar property, a tremendous negative pressure. In Einstein's theory of gravity, negative pressure generates repulsion, and this repulsive gravity would have been the engine of inflation. As long as the inflatoned field remained trapped in this high-energy state known as a false vacuum, it drove an exponential expansion of space. The problem is, we have no direct evidence for the inflatoned field itself. We don't know what kind of particle it corresponds to or its properties. We are essentially reverse engineering its existence from the observable consequences it must have had, namely, a flat, smooth universe with the specific kind of density fluctuations we observe. The how of inflation remains one of the great unsolved mysteries in particle cosmology. Different models propose different shapes for the inflatoned field's potential energy. Was it a gentle slope leading to a slow roll and a long period of inflation? Or was it a more complex landscape with sharp features that could have left distinct imprints on the universe? The specifics matter enormously because they determine the precise statistical properties of the quantum fluctuations that got stretched into cosmic structures. While the overall prediction of a nearly scale invariant spectrum of fluctuations is a triumph of inflation, the detailed nuances could distinguish between countless possible inflationary models. This search for the mechanism is not just academic, it connects to the very nature of reality. Some models of inflation are eternal, suggesting that once started, inflation never completely stops, giving rise to a vast multiverse where our universe is just one bubble among infinite others. If this is the case, then the initial conditions that made our universe so smooth were not a unique, one-time event, but a local outcome in a much grander, ongoing process. The horizon problem and its inflationary solution therefore stand as a pivotal moment in our cosmic narrative. We have moved from a puzzle about smoothness to a profound, albeit unproven, theory about the universe's violent birth. We know that the universe is smooth, and we have a brilliant idea for how it became that way, but the fundamental physics behind that transformative event remains one of the most important missing pieces in our understanding of the cosmos's initial expansion. And so we arrive at a finding so peculiar that it has earned an ominous nickname straight out of a science fiction thriller, the axis of evil. This isn't a cosmic battle station, but something potentially far more unsettling, a series of strange, large-scale anomalies in the cosmic microwave background that, if confirmed, could imply our universe has a preferred direction, a fundamental lopsidedness that violates a cornerstone of modern cosmology. The principle of isotropy, the idea that the universe looks the same in every direction, is a foundational pillar of the Standard Model. It's why we expect the cosmic microwave background to be a nearly perfect, uniform sphere of ancient light, with only the tiny, random fluctuations that seeded today's galaxies. For the most part, it is, but when scientists began analyzing the full sky maps from satellites like WMAP and Planck with exquisite precision, they noticed weird patterns that simply shouldn't be there. The most prominent of these is an alignment, a curious correlation between the hot and cold spots on the sky. Imagine throwing a handful of confetti onto a perfectly round ball. You'd expect the pieces to land in a random, chaotic scatter. Now, imagine instead that a surprising number of those pieces line up along a single, great circle around the ball, as if someone had drawn a faint equator and the confetti felt a strange urge to align with it. That's essentially what some researchers claim to see in the CMB. The multipoles, the mathematical components that describe the temperature variations, seem to be aligned with each other and with the geometry of our solar system in a way that is deeply unnatural. This apparent preferred axis, this axis of evil, seems to point in a specific direction in space, roughly aligned with the ecliptic plane, the path the planets take around the Sun. The immediate and most likely explanation is that this is a colossal statistical fluke combined with an unaccounted for systematic error. Our universe is, after all, one single realization. We only have one CMB sky to observe, and it's possible that by pure chance the random fluctuations just happen to line up in this strange way. Furthermore, perhaps our own backyard is contaminating the signal. Subtle effects from the dust in our solar system, or even the way our spacecraft moves and observes, could potentially imprint a faint, directional bias onto the data that we haven't perfectly cleaned away. The scientific community is therefore rightly skeptical, and most cosmologists lean toward this being a combination of chance and overlooked systematics. But the anomalies have proven stubborn. They persist even after the teams behind the Planck mission have performed Herculean efforts to clean their data of every conceivable local contaminant. This persistence forces us to consider a far more radical possibility. What if the signal is real? What if the universe on its largest scales is not isotropic? The implications would be revolutionary, challenging not only the cosmological principle but also our understanding of inflation. The entire point of inflation was to take a tiny, connected patch of the early universe and blow it up so large that it appears flat, smooth, and featureless from our limited viewpoint. But if these large-scale anomalies are genuine, they could be a fossil, a cosmic scar from a time before inflation began. Perhaps the universe that inflated was not perfectly smooth. Maybe it had some primordial texture, a pre-existing asymmetry, or a giant gravitational wave stretching across the infant cosmos. When inflation blew everything up, it would have stretched this initial imperfection to a scale so vast that we can only just perceive its ghostly outline across our entire observable horizon. In this scenario, the axis of evil is not an axis of anything sinister, but a relic of the universe's messy birth, a fingerprint of the conditions that existed before inflation did its work of smoothing everything out. It would be a window into the ultimate origin of everything, a clue that the cosmos we inhabit carries the indelible mark of its very first moments, a directional memory imprinted into the expansion geometry of spacetime itself. The debate rages on, a tense standoff between the compelling simplicity of our standard model and the tantalizing, if unproven, whispers from the data that suggest there is a profound and mysterious directionality woven into the fabric of our universe. But to truly trust the shocking conclusion that the universe is accelerating, we must have absolute faith in our cosmic yardsticks. This brings us to a deeply unsettling question that strikes at the very core of our measurements. Could we be fundamentally wrong about the vast distances we've assigned to the cosmos? The entire edifice of modern cosmology rests upon a delicate and intricate structure known as the cosmic distance ladder. It's a brilliant step-by-step process where each rung is calibrated by the one below it, allowing us to climb from the familiar confines of our solar system out to the most remote galaxies. But if there is even a tiny, hidden crack in one of these rungs, the entire structure could wobble, and with it, our understanding of the universe's expansion. The most critical rungs in this ladder, the ones that directly revealed the acceleration, are Cepheids variable stars and Type 1, a supernova. Cepheids are our first major step into intergalactic space. These are pulsating stars whose intrinsic brightness is directly tied to their pulsation period. A Cepheid that takes longer to brighten and dim is inherently more luminous than one with a quick pulse. By measuring the period of a Cepheid in a relatively nearby galaxy, astronomers can determine its true wattage. Then, by comparing that known luminosity to how faint it appears from Earth, they can calculate its distance with remarkable precision. It's like knowing the true power of a specific lighthouse bulb. By seeing how dim it looks on the horizon, you can gauge how far away the shore must be. These Cepheid distances are then used to calibrate the next, even more powerful rung on the ladder, Type 1, a supernova. These stellar explosions are the most crucial standard candles for measuring the deep universe. They occur in binary star systems where a white dwarf siphons material from its companion until it reaches a critical mass limit, triggering a thermonuclear explosion that is always, in theory, of the same peak brightness. Because they are so incredibly luminous, outshining entire galaxies, we can see them across billions of light years. and because they all have the same intrinsic brightness, their apparent dimness is a direct and powerful measure of their distance. This is the chain of reasoning that led to the discovery of dark energy. The most distant supernovae were fainter than expected, meaning they were farther away than our models predicted, forcing the conclusion that the expansion is accelerating. But this entire chain of logic is only as strong as its calibration. The absolute brightness of those crucial Type 1a supernova is set by measurements of Cepheid variables in the same host galaxies. This is where a potentially catastrophic systematic error could creep in. What if our understanding of Cepheids is subtly flawed? These stars don't exist in a perfect vacuum. They are often found in dusty regions of galaxies. Interstellar dust doesn't block light completely. It scatters and reddens it, much like the sun appears redder at sunset as its light passes through more of Earth's atmosphere. If we misjudge the amount of this dust extinction, we will misjudge the true, undimmed brightness of the Cepheid. If we think a Cepheid is dimmer due to distance, but it's actually dimmer because of dust, we will incorrectly calculate that it is farther away than it truly is. This single error would then propagate up the entire ladder. A miscalibrated Cepheid would lead us to assign the wrong intrinsic brightness to the Type 1a supernova in that galaxy. If we think those supernovae are intrinsically brighter than they actually are, then when we see a distant, faint supernova, we would assume it is even more distant than it truly is. This would create a phantom signal of acceleration, making it seem as if the universe was speeding up when in reality it was just our measurements that were off. This is not a trivial concern. In recent years, two of the most powerful telescopes in history, the Hubble Space Telescope and the new James Webb Space Telescope, have been focused on this very problem in a project called SHOES. The goal is to measure Cepheids with unprecedented precision, cross-checking them against other distance markers like the parallax of nearby stars and a type of star called the tip of the red giant branch. The James Webb Telescope, with its infrared eyes, is particularly powerful for this task because infrared light cuts through dust much more effectively than visible light. By observing Cepheids in the infrared, we can get a cleaner, less dusty measurement of their true brightness. The initial results from James Webb have only sharpened the Hubble tension, confirming the Hubble Space Telescope's measurements with even greater confidence. This suggests that dust is likely not the primary villain in this story, but the investigation is far from over. There are also potential issues with the supernova themselves. We call them standardizable candles, not perfect standard candles. Their peak brightness has a small natural variation, but we can correct for it by looking at the shape of their light curve, how quickly they brighten and fade. A supernova that declines more slowly is slightly more luminous, but what if this correction isn't perfect? What if the properties of the white dwarfs or their environments have evolved over cosmic time? The supernova we see in the nearby universe are younger than those in the far distant early universe. It's conceivable that the metallicity, the abundance of elements heavier than hydrogen and helium, was different in the first stars, and this could have subtly affected the explosion mechanism of early supernova, making them intrinsically fainter or brighter than their modern counterparts. If distant supernova were systematically fainter for reasons other than distance, it would again create a false impression of acceleration. The astronomical community is tackling this from every angle, searching for any possible systematic bias that could resolve the tension. They are using entirely different methods to build the distance ladder, such as using the surface brightness fluctuations of galaxies or the water maser emissions from megamasers in galactic nuclei. Each independent method provides a cross-check on the Cepheid supernova chain. So far, the different paths are not converging to a single, lower value for the Hubble constant. Instead, they are largely reinforcing the divide, with local distance ladder methods consistently giving a higher expansion rate than the early universe predictions from the cosmic microwave background. The persistence of the Hubble tension despite these Herculean efforts to find an error is in a way the most compelling argument that it might be real. It suggests that the problem is not with our yardsticks but with our map of the cosmos. We may be forced to conclude that our measurements are correct and that the universe is simply more mysterious than we imagined. Its expansion rate a genuine puzzle that points toward new physics beyond our current model. Now, let's connect the grand story of cosmic expansion to the very building blocks of matter by looking at a mystery that arises from the universe's first few minutes. This is known as the lithium problem, and it's a quiet but persistent crack in our otherwise remarkably successful model of the Big Bang. To understand it, we have to rewind to a time before the first stars, before the cosmic microwave background was released, to a period known as Big Bang nucleosynthesis. This was the universe's first and greatest alchemical event, a brief window when the entire cosmos was hot and dense enough to act as a nuclear fusion reactor. For about the first 20 minutes after the Big Bang, the universe was a seething, opaque soup of protons, neutrons, and other elementary particles. As it expanded and cooled, protons and neutrons began to combine, forging the first atomic nuclei. The models that describe this process are spectacularly successful. They predict the cosmic abundances of the lightest elements with stunning accuracy. The amount of hydrogen we see, the amount of its heavier isotope deuterium, and the amount of helium-4 all match the predictions almost perfectly. This agreement is one of the three great pillars of evidence for the Big Bang theory, alongside the expansion itself and the cosmic microwave background. But there is one glaring, stubborn exception: lithium. Specifically, the isotope lithium-7. Our models of Big Bang nucleosynthesis predict that the primordial universe should have left behind about 3 times more lithium-7 than what we actually observe in the oldest stars in our galaxy. These ancient stellar relics, known as population 2 stars, formed from nearly pristine material, so their atmospheres preserve a fossil record of the universe's original chemical composition. When astronomers measure their lithium content, they consistently find only about a third of what the theory says should be there. It's as if a cosmic accountant has discovered that a massive amount of this primordial element is simply missing from the ledger. This isn't a small, marginal error. It's a discrepancy of several 100%, and it has resisted resolution for decades. So, where did the lithium go? Or was it never made in the expected amounts to begin with? One possibility is that our understanding of the nuclear physics itself is incomplete. The chain of reactions that produces lithium-7 in the early universe is delicate. It primarily forms from the radioactive decay of beryllium-7. If the nuclear reaction rates involved in this chain are even slightly different than what we've measured in laboratories here on Earth, it could throw off the final lithium abundance. Perhaps there is an unknown nuclear resonance, a fleeting, energized state of a nucleus that would have provided a more efficient pathway for destroying lithium-7 as it formed. Physicists have scrutinized these nuclear cross-sections, but so far, no simple adjustment has resolved the problem without ruining the perfect predictions for hydrogen and helium. Another fascinating line of inquiry connects this missing lithium directly to the expansion history of the early universe. The entire process of Big Bang nucleosynthesis was a frantic race against time, dictated by the cooling rate of the expanding cosmos. The moment the temperature dropped below a certain threshold, nuclear reactions effectively froze, locking in the elemental abundances. The predicted amount of each element is therefore exquisitely sensitive to the density of the universe and, crucially, to its expansion rate during those first few minutes. What if something was subtly different about that expansion? Could an unknown form of energy or a new type of particle have been present, altering the expansion rate just enough to change the outcome of this primordial nuclear cook-off? For instance, if there were additional types of neutrinos or some other form of dark radiation, present during nucleosynthesis, it would have caused the universe to expand slightly faster. A faster expansion would have meant that the nuclear freeze-out happened a bit sooner, cutting short the time available for nuclear reactions to build up elements. This could potentially reduce the yield of lithium-7. However, this is a tricky balancing act because a change in the expansion rate would also affect the other light elements like deuterium, which we already measure to be in near-perfect agreement with the standard model. Tweaking the model to fix the lithium problem without breaking the successful predictions for deuterium and helium is a tremendous challenge for cosmologists. There's also the possibility that the lithium wasn't underproduced but was later destroyed. Perhaps these ancient stars we use as cosmic probes are not perfect time capsules. Maybe over their billions of years of life, internal processes like convection have dragged surface lithium down into hotter interior regions where it was fused into heavier elements, systematically depleting the original amount. Astronomers have looked for this, and while some stellar mixing does occur, it's unclear whether it can account for the full, uniform discrepancy seen across so many different ancient stars. The persistence of the lithium problem is a profound reminder that our understanding of the universe's first moments is not yet complete. It serves as a tiny, chemical fossil pointing toward physics that may lie beyond our current standard models. Solving it could reveal new details about the particle content of the infant cosmos or the fundamental nuclear forces at work, providing a unique window into the conditions of the universe during its earliest, most explosive phase of expansion. This idea that the cosmos might have a built-in direction, a cosmic north, directly confronts one of the most sacred principles in all of cosmology, the cosmological principle. This principle, which underpins virtually all of our models, states that on sufficiently large scales, the universe is both homogeneous and isotropic. Homogeneous means the cosmos is roughly the same everywhere. A fair sample of the universe in one region looks like a fair sample in any other. Isotropic means it looks the same in every direction. There is no center, no edge, and no special place or orientation. It's a statement of cosmic humility, asserting that we do not occupy a privileged location in the universe. This principle is why we can apply the same physical laws across billions of light years and expect them to hold true. It's the foundation upon which we built our understanding of the Big Bang and the expanding universe. To find evidence of a preferred direction would be to shake this foundation to its core, suggesting that the very fabric of reality might be woven with a subtle, fundamental grain. The search for this potential directional bias or anisotropy often focuses on a specific type of measurement called a dipole. We're actually already familiar with one major cosmic dipole, the one in the cosmic microwave background. As our solar system moves through space, we're hurtling towards the constellation Leo at a brisk 600 kilometers per second relative to the rest frame of the CMB. This motion creates a Doppler effect, making the CMB appear very slightly hotter in the direction we're heading and cooler in the opposite direction. This is a well-understood local effect due to our own motion, and it's routinely subtracted out of the data to reveal the underlying pristine background. But what if, after we account for our own motion, a residual dipole persists? What if the universe itself, its expansion rate, is not uniform in all directions? This is the startling claim that has emerged from a number of studies over the past decade. Some analyses of large catalogs of galaxies, quasars, and even Type 1, a supernova, have suggested that the expansion of the universe might be slightly faster in one celestial hemisphere and slower in the other. Imagine blowing up a balloon, but instead of it inflating into a perfect sphere, one side seems to bulge out just a little bit more rapidly than the other. On the scale of the entire observable universe, even a tiny percent-level asymmetry would be revolutionary. One of the most intriguing pieces of evidence comes from the very objects that reveal dark energy. When astronomers have analyzed large collections of distant supernovae, some studies have found that the apparent acceleration rate isn't perfectly uniform. The supernova in one half of the sky seem to be ever so slightly dimmer, and therefore farther away than the models predict, while those in the opposite half appear a touch brighter and closer. This could be interpreted as the universe expanding faster in the dimmer direction. Similarly, surveys of hundreds of thousands of quasars have also hinted at a similar dipole in their distribution and properties. These aren't just random fluctuations. The purported axis of this asymmetry, sometimes nicknamed the axis of evil in a different context, seems to align roughly with other, unrelated large-scale anomalies, such as the one we find in the cosmic microwave background. The fact that multiple, independent probes might be pointing toward a similar direction in the sky is what makes this more than just a statistical curiosity. It suggests we might be looking at a coherent, physical effect imprinted on the cosmos, rather than a series of unrelated flukes. So, what could possibly cause the universe to expand at different rates in different directions? The explanations, if the effect is real, are as profound as they are speculative. One possibility is that our universe is not perfectly smooth on scales even larger than what we can observe. The cosmological principle is an assumption, one that works incredibly well within our observable horizon, but it might break down on truly vast superhorizon scales. Imagine our entire observable universe is just one bubble in a vast cosmic foam. What if the bubble next to ours had a slightly different density or a different value for dark energy? The gravitational pull or push from that neighboring, unobservable region could, in theory, tug on our local universe, causing it to expand at a different rate in that particular direction. We would be living inside a slight cosmic gradient, like a hill on the landscape of the multiverse, and we're experiencing a gentle cosmic slope. Another, even more mind-bending possibility involves the primordial universe. Perhaps the initial conditions for inflation were not perfectly symmetric. Maybe the inflattened field that drove the hyper-expansion had a slight directional dependence, a kind of texture that was stretched across the entire sky, leaving a permanent, faint imprint on the expansion rate that has persisted for 13.8 billion years. This would mean that the isotropy we take for granted was never truly perfect, and we are now just barely detecting the fossil evidence of that primordial imperfection. Of course, the scientific community remains rightly skeptical. The observed signal is subtle, buried deep within incredibly complex data sets, and is susceptible to all sorts of systematic errors. Could it be that uneven dust distribution in our own Milky Way is dimming supernova more in one part of the sky than another? Might there be calibration differences between telescopes in the northern and southern hemispheres that haven't been fully accounted for? The history of cosmology is littered with anomalies that faded away with better data and more rigorous analysis. The burden of proof for overturning the cosmological principle is astronomically high. Researchers are now employing powerful new tools to test this hypothesis. The Dark Energy Spectroscopic Instrument, or DESI, is mapping tens of millions of galaxies with unprecedented precision, and the Vera-C. Rubin Observatory will soon begin a decade-long survey of the entire southern sky. These projects will provide such an enormous, clean data set that they should be able to either confirm the dipole anomaly with high confidence or, more likely, rule it out definitively. The quest to find a preferred direction is more than a search for a cosmic quirk. It is a fundamental test of our core assumptions about reality. A confirmed detection would mean that the universe is not just expanding, but that it is expanding with a whisper of a preferred direction, a hidden arrow written into the laws of physics themselves, pointing toward a deeper layer of cosmic structure we have only just begun to imagine. Yet this grand synthesis of quantum mechanics and general relativity remains a theoretical dream, and its absence leaves a gaping hole in our understanding of the cosmos, especially when we confront the enigma of dark energy. The cosmological constant, our best model for dark energy, is precisely the kind of vacuum energy that quantum field theory predicts, yet the predicted value is catastrophically wrong. This suggests that a successful theory of quantum gravity must somehow explain why the quantum vacuum gravitates so weakly, or perhaps not at all in the way we expect. Could it be that in a full quantum theory of gravity, the contributions of countless virtual particles cancel out in a way we haven't yet grasped? Or does the emergent nature of spacetime itself provide a mechanism that suppresses the vacuum energy, rendering it nearly, but not perfectly, zero? The tiny, positive value we observe for dark energy could be a residual effect, a leftover whisper from the quantum gravitational processes that shaped the early universe. Without a theory of quantum gravity, dark energy is not just a mystery. It is a screaming symptom of our ignorance, a direct signal that our two most powerful descriptions of reality are fundamentally at odds when applied to the empty space between galaxies. Resolving this conflict is not an abstract exercise for philosophers. It is the essential next step to understanding why the universe is expanding the way it is and what its ultimate fate will be. After all, the story of cosmic expansion is a history of adding invisible components to our universe. First, we discovered that the visible stars and galaxies were not enough to explain the gravitational glue holding clusters together, so we invented dark matter. Then we found that all the matter we knew of, both light and dark, could not explain the accelerating expansion, so we invoked dark energy. These two invisible entities now make up 95% of the entire cosmos. But what if our current list of ingredients is still incomplete? What if dark energy and dark matter are not the final, fundamental answers, but are themselves merely symptoms of a deeper, more profound reality that we have not yet even begun to fathom? It is a humbling and thrilling possibility that we are still missing a major piece of the cosmic puzzle, a hidden component that could be influencing the expansion in ways we haven't yet conceived. This isn't just about refining our measurements of what we already know. It's about being open to the existence of something entirely new, a form of matter, energy, or even a modification to the fabric of reality that operates outside the current paradigms of physics. Consider the strange and persistent anomalies that our standard model struggles to explain. The Hubble tension, that stubborn discrepancy in the expansion rate, could be more than just a calibration error. It might be a direct signal that the universe's expansion history is not what our simple model of dark matter and a cosmological constant predicts. Perhaps there is a third, dynamic agent at play, a component that briefly influenced the early universe and then decayed away, or one that is only now beginning to assert its influence. Imagine a cosmic field that interacts only very weakly with both dark matter and normal matter, but whose energy density evolved in a specific way, subtly changing the sound horizon at the time of the cosmic microwave background and leaving a different prediction for today's expansion rate. Such a field wouldn't fit neatly into our existing boxes of matter or dark energy. It would be something entirely new, a relic from the universe's earliest moments that we are only now detecting indirectly through its lingering effect on the Hubble constant. Another fascinating possibility lies in the realm of unification. Our current physics is a patchwork of separate theories, the standard model for particles and general relativity for gravity. String theory and other approaches to quantum gravity suggest that at the highest energies, all forces and particles are unified. In this theoretical landscape, the early universe would have been dominated by a plethora of exotic fields and particles that have since vanished or condensed into the forms we see today. Could one of these primordial relics have survived in a diluted form to the present day? Perhaps what we call dark energy is not a simple cosmological constant, but the low-energy remnant of a much richer, dynamic field from the string theory landscape. These theories often predict not one, but many scalar fields similar to the hypothesized inflaton that drove the Big Bang's inflation. one of these fields could have remained largely dormant for billions of years, only to recently start dominating the cosmic energy budget, causing the acceleration we see. This would make dark energy a cousin of the inflation field, a late-time activation of a cosmic force that has been waiting in the wings since the universe began. Even more speculative is the idea that dark matter itself might be more complex than a single, simple particle. What if the dark sector is as rich and varied as the visible sector? We have protons, electrons, neutrinos, and photons all interacting in complex ways. Why should the dark universe be any different? There could be multiple types of dark matter particles, some that are cold and slow-moving, and others that are warm or even interact through their own dark force. This complex dark sector could have undergone phase transitions of its own throughout cosmic history, releasing energy or changing its equation of state in ways that would have left an imprint on the expansion rate. The acceleration of the universe might not be due to a separate dark energy at all, but rather a consequence of the complex internal dynamics of the dark world itself. Furthermore, some of the most profound mysteries point toward a potential connection between the very small and the very large that we have yet to understand. The cosmological constant problem, the fact that the calculated vacuum energy is 120 orders of magnitude larger than observed, is the single biggest mismatch in all of science. This isn't just a small error, it is a scream from nature that our understanding of quantum fields and gravity is fundamentally broken. Resolving it will likely require a revolution, and that revolution could easily introduce new cosmic components or principles that radically alter our story of expansion. Perhaps the vacuum energy is cancelled not by a symmetry, but by a new, undiscovered field. Or maybe the universe has a built-in mechanism that prevents the vacuum from gravitating in the way we expect, a principle that would inevitably introduce new terms into the equations governing the cosmos. Stepping back, the very fact that we have had to invent dark matter and dark energy to make our equations work should give us pause. It reveals a pattern. When our observations don't match our predictions, we add a new, invisible component. While this has been a successful strategy so far, it also highlights the provisional nature of our knowledge. The history of science is filled with examples where anomalies that were explained by adding new elements were later understood through a more fundamental shift in perspective. The orbit of Mercury was eventually explained not by an unseen planet, but by a new theory of gravity general relativity. Could our current dark universe be a similar prelude to a much deeper revolution? Are we like astronomers before Einstein, meticulously charting the motions of planets and inventing complex epicycles to explain their paths, all the while missing the simple, elegant truth of curved spacetime? The search for this missing component is what drives the next generation of cosmic observatories. Telescopes like the Vera C, Rubin Observatory and the Euclid Space Telescope are not just designed to measure dark energy more precisely. They are discovery machines built to uncover anomalies in the growth of cosmic structure that could point the way to entirely new physics. They are looking for any deviation from the predicted script, any wrinkle in the data that whispers of a presence we haven't yet named. To contemplate that we might be missing a major component of the universe is to embrace the most exciting aspect of science, its boundless potential for surprise. It acknowledges that the cosmos is under no obligation to be simple or to conform to our current limited categories. The true engine of cosmic expansion may not be dark energy as we currently imagine it, but something far more strange and wonderful, a hidden player in the cosmic drama waiting for its moment to step into the light. And so, after this grand tour of cosmic mysteries, from the quantum foam of spacetime to the vast, dark energy-dominated future, we are left with one final, overarching question that ties all the others together. Will we ever find a unified answer? The sheer number of puzzles we've explored, 25, and these are just the beginning, might feel overwhelming, even discouraging. But look closer and you'll see they are not isolated curiosities. They are pieces of a single, magnificent puzzle. They are interconnected in a delicate cosmic web where pulling on one thread often tightens or loosens several others. Consider the central enigma of dark energy. Unlocking its true nature, whether it is a simple cosmological constant, a dynamic quintessence field, or a sign that gravity itself needs revision, wouldn't just solve one problem. It would send shockwaves through our entire understanding of cosmology. A definitive answer to dark energy would immediately reshape our predictions for the ultimate fate of the universe, directly addressing our second and third questions. It would also provide crucial context for the Hubble tension. If dark energy is more complex than we thought, its evolving strength could perfectly explain why the local and early universe measurements of expansion don't align. Solving the dark energy puzzle could even shed light on the cosmological constant problem, that catastrophic mismatch between quantum theory and observation, perhaps by revealing a new symmetry or a deeper principle that suppresses the vacuum energy. This cascade effect doesn't stop there. Imagine if we finally detect a candidate for dark matter. Identifying this invisible scaffolding of the cosmos would not only tell us what 27% of the universe is made of, but it would also refine our models of structure formation. This, in turn, would give us a more precise history of how the cosmic expansion transitioned from deceleration to acceleration, offering another independent test for the properties of dark energy. Or consider the hunt for primordial gravitational waves, the faint ripples from inflation. Detecting them would be a direct probe of the universe's first moment of expansion, potentially validating inflation and telling us about the energy scales at which the inflaton field operated. This could narrow down the list of viable grand unified theories and, by extension, inform our models of the early universe conditions that set the stage for everything that followed, from the lithium problem to the formation of topological defects. This profound interconnectedness is the reason for both great frustration and tremendous hope. It means that a single, elegant discovery has the power to unravel multiple knots at once, collapsing a whole branch of mysteries into a coherent picture. The quest for this unified understanding is the driving force behind a new era of astronomical exploration, an era defined by telescopes and instruments of such breathtaking power that they are, in essence, time machines designed to read the universe's story with unprecedented clarity. The Vera C. Rubin Observatory, with its colossal camera that will photograph the entire visible southern sky every few nights, will catalogue billions of galaxies, mapping the cosmic web in more detail than ever before. By tracking how the large-scale structure of the universe has grown and evolved, it will put stringent new constraints on the properties of dark energy and dark matter, testing whether general relativity truly holds on the largest scales. The Nancy Grace Roman Space Telescope will join this effort with a panoramic view of the infrared sky, peering back to the epoch when dark energy first began to dominate the cosmos, providing a critical movie of the universe's accelerating expansion. Meanwhile, the European Space Agency's Euclid spacecraft is already surveying the sky to create a gigantic 3D map of the universe, using both galaxy positions and the subtle distortions of their light from gravitational lensing to weigh the invisible dark matter and measure the influence of dark energy across 10 billion years of cosmic history. And on the ground, the Dark Energy Spectroscopic Instrument, or DESI, is precisely measuring the redshifts of tens of millions of galaxies, reconstructing the expansion history with such precision that it could finally resolve the Hubble tension, or perhaps deepen it into an even more profound crisis that demands new physics. But the search doesn't end with these optical behemoths. The Laser Interferometer Space Antenna, or LISA, a future space-based gravitational wave observatory, will open an entirely new window onto the cosmos. By detecting the low-frequency hum of merging supermassive black holes and the faint echoes from cosmic strings, If they exist, Lisa will probe the universe in a way that light alone never can, giving us a direct sense of how spacetime itself is stretched and warped by the most violent events, offering yet another independent test of our cosmological models. And peering back to the very beginning, next-generation telescopes like the Simons Observatory and CMB-S4 will stare at the cosmic microwave background with such exquisite sensitivity that they might detect the faint, curled polarization pattern of primordial gravitational waves, the smoking gun for inflation. This single measurement would tell us about the energy scale of the universe's birth, directly confronting the theories of quantum gravity and perhaps even offering a glimpse into the multiverse. The goal of this entire, coordinated, global scientific endeavor is not merely to collect more data, but to weave it into a complete theory of the universe's expansion. A theory that can explain the initial inflationary burst, the transition to the slow, matter-dominated crawl, and the final, mysterious acceleration, all within one consistent framework that seamlessly connects the quantum world. With a cosmic scale, such a theory would represent one of the greatest achievements of the human intellect, a true theory of everything for the cosmos as a whole. The journey to get there is far from over. We may find that our current categories of dark matter and dark energy are merely placeholders for something far more strange, a unified dark sector or a modification of physics that we have not yet conceived. The path may lead us through a labyrinth of false leads and confusing anomalies, but each wrong turn and each dead end teaches us something invaluable about the landscape of reality. The pursuit itself, this collective human effort to understand our place in this vast, expanding universe, is a story as compelling as any of the answers we might one day find. We are cosmic archaeologists sifting through the relics of the past and cosmic prophets, trying to read the destiny of the future, all in the hope of answering the most fundamental question of all. What is this cosmos we call home, and what forces guide its magnificent, unfolding story? So as we reach the end of this cosmic journey, it's worth pausing to reflect on what this entire exploration truly means. We have ventured through 25 profound mysteries, from the ghostly pull of dark matter and the phantom push of dark energy, to the stubborn Hubble tension and the enigmatic lithium problem. We have grappled with the possibility of a multiverse, questioned the constancy of physical laws, and stared into the abyss of a pre-Big Bang reality. Yet, the most breathtaking realization is not the individual answers we might one day find, but the staggering, humbling scope of our collective ignorance. For every question we've explored, we've uncovered two more lurking in the shadows. Our most sophisticated models, our most powerful telescopes, and our brightest minds have only managed to chart about 5% of the cosmic ocean. The remaining 95% is a vast, uncharted sea of dark matter and dark energy, whose fundamental nature remains completely unknown to us. This isn't a sign of failure. It is a testament to the sheer grandeur and complexity of the universe we are privileged to inhabit. Our understanding of cosmic expansion is not mature or complete. It is still in its infancy, taking its first tentative steps into a cosmos far stranger and more wonderful than we ever imagined. This entire edifice of modern cosmology, built over a century of discovery, rests upon foundations that are themselves mysterious. We use general relativity to describe the cosmos, yet we don't have a quantum theory of gravity to explain its earliest moments. We have a detailed map of the cosmic microwave background, yet it contains anomalies like the axis of evil that whisper of a deeper layer of reality we can't yet decipher. We can trace the history of the universe back to a fraction of a second after the Big Bang, but the ultimate origin of space and time themselves remains the greatest enigma of all. Each puzzle we've discussed is a single thread in a magnificent, interconnected tapestry. Pulling on the thread of dark energy tightens the knot of the Hubble tension. Tugging on the nature of inflation forces us to reconsider the ultimate fate of the cosmos. This beautiful, intricate web of questions shows that we are not dealing with a list of isolated problems, but with a single, unified mystery, the nature of reality itself. The fact that we can even formulate these questions, that we can build tools like the James Webb Space Telescope to peer back to the dawn of the first galaxies, and that we can devise mathematical frameworks like string theory to probe the Planck epoch, is a triumph of human curiosity and ingenuity. We are a species born on a tiny, rocky planet orbiting an average star in a quiet corner of a galaxy, and yet we have managed to reconstruct the history of the entire observable universe and identify the profound gaps in that story. This journey of cosmic discovery is one of the most inspiring narratives we have ever told ourselves. It is a story that belongs not just to scientists in lab coats, but to all of us. Every time you look up at a clear, dark night sky, you are gazing directly at this unfolding mystery. Those points of light are not just stars, they are distant suns whose light has traveled for years, centuries, even millennia to reach your eyes. The vast darkness between them is not mere emptiness, it is the expanding fabric of space-time, filled with the invisible architecture of dark matter and propelled by the mysterious engine of dark energy. You are a living, conscious part of this grand cosmic drama, connected to the birth of stars and the fate of galaxies. So let this not be an end, but an invitation. Stay curious, follow the journey of discovery as new telescopes, new theories, and new generations of explorers continue to push the boundaries of the known. The next great cosmological revelation might come from a revolutionary data set from the Vera C. Rubin Observatory, a brilliant theoretical insight from a student yet unknown, or perhaps even an unexpected observation from an amateur astronomer gazing up at the stars from their own backyard. The universe is under no obligation to make sense to us, but our relentless drive to understand it is what makes us human. Keep looking up, keep wondering. For in the words of the great astronomer Carl Sagan, the cosmos is within us, we are made of star stuff, we are a way for the cosmos to know itself. The story of the expanding universe is our story, and the next chapter